our own Earth, this beautiful sphere of blue and white floating in the immense quiet of space, may not represent the pinnacle of planetary habitability. Tonight, we are exploring a truly profound realization in modern astronomy: the discovery of worlds that could be even more welcoming to life than our own. These are not merely planets that might harbor life, but worlds potentially better equipped for it to flourish. This is a finding that gently reorients our perspective on what constitutes a perfect environment for complex biospheres to thrive. If you find a sense of peace in these quiet journeys through science, your support by subscribing and liking this video is deeply appreciated. The visuals are here to guide you, but you are welcome to simply close your eyes, breathe, and allow your mind to wander among the stars as we investigate these incredible places. I also invite you to share where you are listening from in the comments, creating a quiet connection on this shared cosmic exploration. For generations, astronomers have scanned the heavens, searching for worlds that mirror our own. The search has centered on finding Earth-sized planets within the orbital path of sun-like stars, where temperatures would permit liquid water to pool on their surfaces. This region, widely known as the Goldilocks zone, has been the primary guide in our quest for other living worlds, a place not too warm, not too cold, but precisely suited for life as we understand it. But the story now takes an unexpected and fascinating turn. What if this entire framework has been too restrictive? Is it possible that in our quest for a reflection of Earth, we have overlooked planets that might offer a superior home for life? Dr. Dirk Schulze-Makuch, an astrobiologist at Washington State University, articulates this idea well, suggesting that we may be missing planets that are even more ideally suited for life than Earth. This concept is not born from speculation. It is the result of methodical scientific review of the thousands of exoplanets catalogued beyond our solar system. Consider for a moment our own planet's history. Earth has endured mass extinctions, profound ice ages, devastating asteroid strikes, and a host of other cataclysmic events that have challenged or even erased entire lineages of species. The habitability of our world has wavered dramatically across billions of years. It leads one to wonder if there are other worlds that provide more constant, more nurturing conditions for life to emerge and prosper. Scientists have now devised a new index for habitability, one that moves well beyond the simple concept of the Goldilocks zone. This more nuanced framework takes into account a range of factors, including the composition of a planet's atmosphere, the levels of radiation from its star, its geological activity, and the dynamics of its orbit. When this new methodology was applied to the vast database of known exoplanets, a remarkable pattern came into focus. A number of these distant worlds registered higher on the habitability scale than Earth itself. On this new index, our planet was assigned a rating of 0.829, yet there are exoplanets out there with scores of 0.836 and even greater. While the difference may appear slight, in the exacting field of planetary science, these decimal places signify substantial improvements in the conditions that allow life to thrive. Let us imagine what one of these superhabitable planets might be like. Picture a world that is slightly larger than our own, perhaps with a radius about 10% greater. This additional size would offer more surface area, allowing for a greater diversity of ecosystems to form. Its increased mass would also create a stronger gravitational pull, enabling the planet to hold on to its precious atmosphere for billions of years longer than Earth is expected to. Now, visualize this world as it orbits not a star like our Sun, but an orange dwarf. These K-type stars are smaller and burn cooler than our Sun, but a key detail is that they live for a much longer time. Our Sun has a lifespan of around 10 billion years, whereas orange dwarfs can shine with stability for 18 to 34 billion years. This is a time span nearly 4 times longer, offering a vastly expanded window for life to evolve, to adapt, and to achieve degrees of complexity we can only begin to contemplate. These orange dwarf stars also emit a very specific amount of ultraviolet radiation. There is enough to fuel essential biological processes, but not so much that life would require the shielding of a dense ozone layer. The lower UV output translates to less damage to DNA, which could permit a more stable course for genetic evolution over immense geological timescales. Now, imagine this superhabitable world possesses a surface temperature just 5 degrees Celsius warmer than Earth's average. This seemingly small increase would foster a more humid, tropical climate across a larger portion of the planet, Higher levels of humidity could in turn sustain more abundant vegetation and more productive ecosystems. The extra warmth would also likely prevent the formation of vast polar ice caps, thereby maximizing the total amount of habitable land available for life to spread and colonize. The atmosphere of such a world could contain 25% oxygen compared to Earth's 21%. This elevated oxygen concentration would act as a powerful catalyst for biological activity. Plants would perform photosynthesis with greater efficiency. Animals would have more metabolic energy at their disposal for developing complex behaviors and for rapid evolutionary change. The entire biosphere would be more dynamic and productive than anything we have witnessed on our own planet. But what is perhaps the most intriguing characteristic is that this superhabitable world would possess a longer geological history than Earth. Being older provides more time for the slow dance of plate tectonics to shape diverse landscapes, for evolution to cultivate an incredible richness of biodiversity, and for intricate ecosystems to achieve stability and maturity. While Earth is approximately 4.5 billion years old, some of these potential superhabitable candidates might be 6, 7, or even 8 billion years old. Reflect on what life on Earth has managed to accomplish in just 4.5 billion years. It has journeyed from simple, single-celled organisms to the staggering complexity of our modern ecosystems, from the very first photosynthetic bacteria to the emergence of human civilization. Now, try to envision what might become possible with several billion additional years of uninterrupted evolution, all taking place on a world with fundamentally superior environmental conditions. These are not merely abstract possibilities. We've already pinpointed specific worlds that appear to meet these criteria. One such example is Kepler 442b, a planet situated approximately 1,200 light-years from our solar system. A super-Earth circles an orange dwarf star from a distance that allows for the perfect influx of energy, potentially sustaining liquid water across its surface. What stands out is its habitability rating of 0.836, a score that, on a new assessment scale, actually surpasses that of our own planet. Another compelling candidate is the newly found GJ251c, a super-Earth located a mere 20 light-years from our solar system. This world possesses nearly 4 times Earth's mass and seems to share a similar rocky makeup. Its position within the life-friendly region of a red dwarf star suggests it could offer the kind of stable, enduring environment needed for life to develop in ways that might eclipse anything seen on Earth. Perhaps the most intriguing find is Gliese 12b, an Earth-like world just 40 light-years away. This planet is slightly smaller than our own, but receives the ideal amount of energy from its host star to maintain surface temperatures around 42 degrees Celsius. If this world has managed to hold onto an atmosphere, it could be a tropical haven with conditions perfectly suited for abundant life. The TRAPPIST, one system, in turn, presents us with an entire family of worlds with superhabitable potential. 7 planets, each about the size of Earth, orbit this small red dwarf, and up to 4 of them may reside within the habitable zone. TRAPPIST 1e is considered particularly promising, as it receives about 60% of the stellar energy that Earth gets from the Sunday. This reduced energy input could foster more stable climate conditions, free from the extreme weather patterns that have triggered mass extinctions on our world. What makes these discoveries truly revolutionary is how they are reshaping our entire approach to the search for life in the universe. For decades, we operated under the guiding assumption that Earth represented the gold standard for habitability. We consistently looked for planets that mirrored our own as closely as possible, thinking that familiar conditions would give us the best chance of finding life. We are now realizing that this Earth-centric bias might have been holding us back. By focusing so intensely on finding exact copies of our own world, we may have been overlooking planets that could support life forms more diverse, more abundant, and more resilient than anything that has ever existed on Earth. The implications are significant. If superhabitable planets are relatively common throughout our galaxy, then the universe might be far more alive than we ever dared to imagine. These worlds could be teeming with ecosystems that make Earth's rainforests look sparse by comparison. They could be home to evolutionary processes that have been running for billions of years, far longer than anything on our planet. The search for these superhabitable worlds is being revolutionized by new technologies and observational techniques. NASA's James Webb Space Telescope can analyze the atmospheres of distant exoplanets, looking for chemical signatures that might indicate not just the presence of life, but of thriving, abundant life. The Transiting Exoplanet Survey satellite continues to discover new candidate worlds at an unprecedented rate. At the same time, ground-based observatories equipped with advanced spectrographs can detect the subtle gravitational wobbles that planets induce in their host stars, allowing us to measure planetary masses with incredible precision. When combined with size measurements from transit observations, we can determine which worlds have the rocky composition necessary to support surface life. More remarkably, we are beginning to detect atmospheric compositions that could indicate superhabitable conditions, including planets with higher oxygen concentrations, increased water vapor content, and atmospheric chemistries that suggest robust biological activity. These are not just potentially habitable worlds. They are worlds where life might be thriving in ways that surpass anything in Earth's history. The closest of these superhabitable candidates is Proxima Centauri b, just over 4 light-years away. This Earth-mass world orbits in the habitable zone of the nearest star to our Sunday. It receives about 65% of the energy that Earth gets, which could create more stable climate conditions. Depending on its atmospheric evolution, Proxima b could have vast oceans and an oxygen-rich atmosphere, supporting ecosystems more diverse than anything on Earth. Scientists are already planning missions to study these worlds in detail. Future space telescopes will be able to analyze their atmospheric compositions, search for biosignatures, and even potentially detect surface features that might indicate the presence of life. Within the next decade, we might know definitively whether some of these superhabitable planets are indeed more hospitable to life than our own world. The implications extend far beyond astronomy and astrobiology. If we confirm that superhabitable planets exist and are relatively common, it would represent one of the most significant discoveries in human history. It would tell us that the universe is not only alive, but that it is far more alive than we ever imagined. These worlds challenge our assumptions about what makes a planet perfect for life. They suggest that the conditions we consider normal and optimal on Earth might actually be somewhat limited compared to what is possible elsewhere in the galaxy. Earth might be a good planet for life, but not necessarily the best. As we continue our exploration of these remarkable worlds, we will discover how scientists are identifying the specific characteristics that make a planet superhabitable, how we are detecting and studying these distant worlds with unprecedented precision, and what the existence of superhabitable planets might mean for the future of life in the universe. The detection of these worlds represents a fundamental shift in how we understand planetary formation and stellar evolution. When astronomers first began discovering exoplanets in the 1990s, they found mostly what we call hot Jupiters, massive gas giants orbiting impossibly close to their host stars. These worlds taught us that planetary systems could be radically different from our own solar system, but they seemed utterly hostile to life as we know it. As our capacity for planetary detection grew more sophisticated, we began to uncover smaller, rockier worlds orbiting within the habitable zones of their stars. Each of these discoveries brought a wave of excitement, yet it also surfaced a persistent and fundamental question within the astronomical community. Were we merely identifying more variations of our own planet, or could life emerge and thrive under a completely different set of circumstances? The answer would arrive from an unexpected shift in perspective. Instead of simply cataloguing worlds that resembled Earth, scientists started to ask a much deeper question. They wondered if our own planet was not the ultimate template for a life-bearing world. Perhaps the conditions that gave rise to life here represented just one of many possible pathways, and not necessarily the most favorable one. This revolutionary thinking led researchers to re-examine the characteristics truly vital for supporting complex, long-lasting biospheres. They looked beyond the basic presence of liquid water and began to weigh factors such as atmospheric stability, the longevity of a host star, geological activity, and orbital dynamics. What came into view was a new vision of planetary habitability. It was a picture far more nuanced and compelling than anyone had previously imagined. Consider the role that a planet's mass plays in establishing superhabitable conditions. Earth's own mass generates sufficient gravity to hold onto our atmosphere, but this hold is somewhat tenuous. Over geological time, our planet is slowly bleeding its atmospheric envelope into space. A world that was 10 to 50% more massive than Earth would exert a stronger gravitational grip. This superior binding force would allow it to retain its atmosphere for vastly longer periods, potentially supporting life for billions of years beyond Earth's projected habitable lifetime. The increased mass also fuels more vigorous geological activity, a result of enhanced radioactive decay deep in the planet's interior. This more enduring internal engine would power plate tectonics for extended eras, recycling essential nutrients through the biosphere and maintaining the chemical cycles life depends upon. On Earth, our plate tectonics may well shut down in another billion years as the planet's interior continues to cool. By contrast, a superhabitable world could maintain its active geology for 10 times as long. But perhaps the most intriguing element is how the properties of a star influence a planet's habitability. Our Sun is what astronomers classify as a G-type yellow dwarf star. It has served us well, providing a stable output of energy for billions of years. However, G-type stars have significant limitations when it comes to fostering life over cosmic timescales. The Sun's energy output is steadily increasing due to changes in its core composition. In about 1 billion years, it will be 10% brighter than it is today, an increase sufficient to trigger a runaway greenhouse effect that will boil away our world's oceans. Eventually, our Sun is destined to expand into a red giant, rendering the entire inner solar system uninhabitable. The total window for complex life to exist around a star like our own spans perhaps 8 to 10 billion years. Now, contrast this with K-type orange dwarf stars, which comprise about 12% of all stars in our galaxy. These stellar engines burn their nuclear fuel far more slowly and efficiently than our Sun. They can maintain a stable energy output for 20 to 40 billion years. This provides an immense window of opportunity, nearly 4 times longer for life to evolve and develop complexity. These extended stellar lifetimes mean that superhabitable planets orbiting these stars could host continuous biological evolution for periods that dwarf the entire history of life on Earth. The radiation environment around orange dwarfs also proves more favorable. These stars emit less harmful ultraviolet radiation than our Sun, which reduces the risk of genetic damage to any surface-dwelling organisms. At the same time, they produce enough UV to drive important atmospheric chemistry and biological processes. It is a perfect balance that could allow life to flourish on a planetary surface without requiring the complex ozone layer that protects Earth's biosphere. Another key advantage involves the habitable zones around these orange dwarfs. These zones are remarkably more stable than those around Sun-like stars. As these long-lived stars age, their energy output changes very gradually, keeping planets within the habitable zone for extended periods. Earth will eventually migrate out of our Sun's habitable zone as its solar brightness increases. A superhabitable planet around an orange dwarf, however, could remain in that ideal sweet spot for tens of billions of years. Recent atmospheric modeling has also revealed another crucial advantage of these worlds. Computer simulations suggest these planets could maintain higher humidity levels and more extensive cloud cover than Earth. This enhanced atmospheric moisture content would create more stable global climate patterns. This stability would, in turn, reduce the risk of the extreme climate swings that have triggered mass extinctions throughout Earth's history. Higher humidity also supports more productive ecosystems. One only has to consider the difference between Earth's tropical rainforests and its desert regions. The rainforests teem with biodiversity precisely because of their warm, humid conditions. A superhabitable planet with globally elevated humidity could be a world of incredible abundance. It might be able to support rainforest-like productivity across much larger areas of its surface. The atmospheric composition of superhabitable worlds opens even more intriguing possibilities. While Earth's atmosphere contains 21% oxygen, some models suggest that 25% oxygen could be the optimal concentration for supporting complex life. This higher oxygen level would increase the efficiency of cellular respiration in animals and boost the productivity of photosynthetic plants. Higher oxygen levels would also support larger, more active organisms. During Earth's Carboniferous period, when atmospheric oxygen reached 23%, we saw giant insects and other creatures that could not survive in today's lower oxygen environment. A superhabitable world with sustained high oxygen could therefore support more impressive megafauna throughout its evolutionary history. The carbon dioxide levels on these planets also play a crucial role. Moderate CO2 concentrations help maintain warm global temperatures through the greenhouse effect. At the same time, they also provide the raw material for photosynthesis. The ideal superhabitable world might therefore maintain CO2 levels that are perfectly balanced. This equilibrium would optimize both temperature regulation and biological productivity. Such a world would be a truly remarkable place, fine-tuned for life in ways that may surpass our own. The chemical makeup of an atmosphere, however, is merely one component in the complex equation of a superhabitable world. The specific orbital dynamics of these planets could also present significant benefits when compared to Earth's own, somewhat unpredictable trajectory. Our home world follows a path that is very close to a perfect circle, a characteristic that blesses us with consistent seasons and stable climatic conditions. Yet, some scientific modeling indicates that a modest degree of orbital eccentricity might actually serve to improve a planet's overall habitability. This could be achieved by fostering a wider variety of climate zones and stimulating atmospheric circulation, which would in turn distribute warmth and moisture with greater efficiency. In a similar vein, planets possessing a higher obliquity could offer unique advantages. This means their axis of rotation is tilted more substantially than Earth's 23½ degrees, which would lead to more pronounced seasonal shifts. While this might initially seem to create a less welcoming environment, it could paradoxically encourage a richer biodiversity by generating a greater number of distinct ecological niches and thereby accelerating evolutionary adaptation. The element of age is another factor that warrants particular consideration when contemplating superhabitable planets. Earth itself came into being approximately 4.5 billion years ago, and in the grand scale of geologic time, life appeared with relative speed. However, the emergence of complex, multicellular organisms did not occur until about 600 million years ago, and intelligence on a human scale is a very recent development from the last few million years. What this timeline seems to suggest is that, provided the environmental conditions remain stable, the complexity of life tends to increase as a planet matures. Consequently, superhabitable worlds that are 6, 7, or even 8 billion years old would have benefited from billions of additional years for the processes of evolution to unfold. The degree of biological intricacy and the sheer variety of life on such ancient worlds could be truly astounding. One can imagine ecosystems defined by elaborate interdependencies among thousands of species, evolutionary solutions that appear almost miraculous, and perhaps even forms of consciousness that would far surpass our own cognitive abilities. The geological history of a superhabitable planet also holds the potential for advantages over Earth's own story of development. The continents and ocean basins of our world have been formed by the haphazard collisions of asteroids, periods of intense volcanic activity, and the slow cooling of the planet's interior. Older worlds would have had significantly more time for these geological forces to sculpt ideal arrangements of land and sea, maximizing the potential for life. Imagine continents configured in such a way that they perfectly regulate the global climate, with inland seas and mountain ranges placed to foster the most life-friendly conditions. Picture ocean basins of an ideal depth, with circulation patterns that flawlessly maintain stable temperatures and carry essential nutrients throughout all marine environments. With billions of extra years, geological forces could shape a planet's surface into a configuration far more hospitable than Earth's somewhat arbitrary layout. The protective magnetic field of a superhabitable world might also be far more powerful than what our own planet provides. Earth's magnetic shield, which is generated by the movement of liquid iron in the planetary core, is what protects us from dangerous solar radiation and cosmic rays. Larger planets with more substantial cores could generate magnetic fields that are both stronger and more consistent, offering superior defense for any life on the surface. These more robust magnetic shields would be especially crucial for planets orbiting red dwarf stars. Such stars are known to produce powerful stellar flares that could otherwise erode a planet's atmosphere over time. A superhabitable world, fortified with a powerful magnetic field, could therefore preserve its atmospheric blanket even when faced with the occasional violent outbursts that are characteristic of smaller stars. Meanwhile, the techniques used to find and identify these potential superhabitable worlds are advancing at a truly remarkable rate. The transit photometry method, for instance, which works by detecting the minute dimming of a star's light as a planet crosses in front of it, has already led to the discovery of thousands of exoplanets. But even newer methods are expanding our ability to understand these distant systems. Radial velocity measurements, which track the gravitational pull a planet exerts on its star, can now identify these wobbles with astonishing precision. The espresso spectrograph is capable of measuring changes in stellar motion as slight as 10 centimeters per second, a sensitivity that allows astronomers to find planets with masses similar to Earth's around stars in our cosmic neighborhood. When this data is combined with observations from transits, it reveals the densities of these planets, telling us whether we are observing rocky worlds that could potentially harbor life on their surfaces. The ultimate goal in this field is the direct imaging of exoplanets. This is an incredibly difficult task because of the intense glare from the host stars, but new technologies that employ coronagraphs and adaptive optics are starting to capture actual images of giant planets in orbit around distant suns. In the future, space-based telescopes will be able to apply this capability to smaller, potentially life-bearing worlds. Perhaps the most promising path for studying superhabitable planets lies in atmospheric spectroscopy during transit events. As a planet moves in front of its star from our perspective, a small amount of starlight passes through its atmosphere. This light carries with it subtle chemical fingerprints that can tell us about the atmosphere's composition. The James Webb Space Telescope has already started this work, detecting water vapor, carbon dioxide, and other molecules in the atmospheres of exoplanets. For a truly superhabitable world, this technique could unveil the signs of a superior biosphere, such as heightened oxygen levels, ideal humidity, and a complex atmospheric chemistry. It's even possible that we might find evidence of industrial pollutants or other technosignatures, which would point to the existence of advanced civilizations that have had billions more years to evolve than our own. Statistical studies of the known exoplanet populations are beginning to indicate that worlds qualifying as superhabitable might actually be quite widespread throughout our galaxy. Initial projections estimate that somewhere between 20 to 30% of stars have planets located within their habitable zones. If even a small percentage of these worlds meet the criteria for being superhabitable, the Milky Way could be home to billions of planets where life flourishes in conditions even better than those found on Earth. This potential abundance of superior worlds introduces profound questions about humanity's position in the cosmos. If our own planet represents not an optimal cradle for life, but merely a sufficient one, what does that imply about the pervasiveness of biological complexity across the universe? The answer could be far more extraordinary than we have ever allowed ourselves to imagine. The implications of this possibility extend well beyond simple planetary statistics. If superhabitable worlds are indeed a common feature of the cosmos, we may need to fundamentally reimagine our understanding of how life develops across universal time. It prompts a sobering reflection. After centuries of assuming Earth represents the apex of biological possibility, we may instead inhabit a world that is only marginally suitable for life by a cosmic standard. This new perspective is at once humbling and inspiring, suggesting that life across the galaxy could be substantially more widespread, varied, and sophisticated than our terrestrial experience has led us to imagine. It also opens extraordinary avenues for comprehending what biology might achieve when provided with truly optimal conditions. This realization profoundly affects our strategies for seeking life elsewhere. Traditional approaches have focused on detecting Earth-like biosignatures, such as oxygen found with water vapor, seasonal changes in atmospheric chemistry, or the infrared fingerprints of chlorophyll-based photosynthesis. But if superhabitable planets support more vigorous biospheres, their biological indicators might be dramatically more obvious than any we would expect from Earth-analog worlds. Consider a world where heightened oxygen and perfect humidity foster forest ecosystems so productive they envelop 90% of the land. The atmospheric data from such a planet would practically declare the presence of biological activity across interstellar distances. Seasonal variations in its atmospheric composition would be far more pronounced, as vast continental forests synchronize their cycles of growth and dormancy. The infrared radiance from such dense vegetation would be detectable even with current telescope technology. The biosignatures from these superior worlds might also extend beyond anything we recognize from our own planet's history. Higher atmospheric oxygen could support chemistries entirely unknown to our experience. The enhanced geological activity on these worlds might drive nutrient cycles that create completely novel forms of biological organization. We might discover atmospheric compounds that have no terrestrial equivalent but instead represent the byproducts of alien metabolisms operating under superior environmental conditions. The temporal aspect of superhabitable planets introduces another layer of complexity to our search efforts. While Earth's biosphere has been present for roughly 3.5 billion years, these ancient worlds could host biological systems that have been evolving for 6, 7, or perhaps 8 billion years. The sheer duration of uninterrupted biological evolution could produce ecosystems of staggering sophistication. We only need to reflect on how much Earth's biosphere has transformed in just the last 500 million years since the Cambrian explosion. That period saw the rise of complex multicellular organisms, the colonization of land by plants and animals, the evolution of flight, the development of social behaviors, and ultimately, the emergence of technology using intelligence. Now, imagine what could be possible with an additional 4 billion years of continuous evolution under more favorable environmental conditions. It follows that any civilizations born on these worlds could command technologies far beyond our present achievements. While human civilization has existed for mere thousands of years, intelligent species on these ancient worlds might have had millions or even billions of years to develop their science, technology, and perhaps forms of organization we cannot yet conceive. This possibility brings fascinating considerations to the search for extraterrestrial intelligence. Instead of looking for radio signals or other signatures of early technological development, we might need to search for evidence of mature civilizations that have had geological ages to perfect their relationship with their planetary environment. Such advanced societies may have learned to manage their atmospheric composition with precision, creating artificial biosignatures that optimize planetary conditions for continued biological flourishing. They might have developed energy systems so efficient and clean that they leave no detectable waste heat or electromagnetic signatures. Their presence might be revealed not by pollution or radio signals, but by the subtle perfection of planetary-scale ecological engineering, a search which in turn requires entirely new astronomical methods. We are learning to look for patterns in planetary atmospheric composition that might indicate deliberate management rather than natural processes. We are developing techniques to detect the infrared signatures of advanced materials that do not occur naturally. We are even considering whether certain orbital configurations of multiple planets might represent evidence of large-scale engineering projects. But perhaps most intriguingly, we are beginning to understand that superhabitable planets might support forms of intelligence that operate on completely different principles than human cognition. Earth's evolutionary history has been shaped by periodic mass extinctions, resource limitations, and environmental instability. These pressures have favored an intelligence that excels at rapid adaptation, tool use, and environmental manipulation. Superhabitable worlds, with their stable, nurturing environments, might have fostered the evolution of intelligence optimized for different purposes. We can envision forms of consciousness adept at long-term thought across millennia, or cognitive architectures that prioritize ecological integration and cooperation above competition and environmental control. The possibility that intelligence might evolve differently under superhabitable conditions challenges our assumptions about what to look for when searching for signs of extraterrestrial civilization. For a long time, we have scanned the skies for signals similar to our own radio and television broadcasts, assuming that technological development follows a universal pattern. But civilizations that emerged on superhabitable worlds might have developed along entirely different trajectories. One can only wonder how different human history might have been if Earth had never experienced mass extinctions, ice ages, or resource scarcity. It leads one to contemplate whether humanity's own impulse for discovery and our drive to push past our planetary confines are inevitable outcomes of intelligence. Perhaps an alternative path exists, one where a species might evolve to be more introspective, more deeply woven into its own biosphere, and perhaps unrecognizable to us as intelligent in our current framework. These are not merely philosophical exercises when we consider the real-world challenges of interstellar communication. Should superhabitable worlds foster forms of consciousness profoundly dissimilar to our own, making meaningful contact would likely necessitate completely new paradigms for interspecies dialogue. We might be required to invent methods for identifying and decoding intelligence that functions on different temporal scales, is motivated by different imperatives, and perceives reality through entirely different sensory channels. The techniques we are refining for atmospheric analysis are starting to provide an unparalleled look into the makeup of these distant worlds. Through spectroscopic observation, it is now possible to find trace gases in the atmospheres of exoplanets at concentrations as low as a few parts per million. This remarkable sensitivity creates the potential to identify not only the primary atmospheric constituents, like water vapor and oxygen, but also the more subtle chemical fingerprints that could point to biological or even technological processes. For example, the concurrent detection of both oxygen and methane within a planet's atmosphere serves as a very strong biosignature. This is because these two gases naturally react and would vanish unless they were being constantly replenished by living organisms. On superhabitable worlds, which could feature heightened biological productivity, we might find these biosignature pairs in far greater abundances than would ever be feasible on a planet like Earth. In a similar vein, the discovery of certain industrial chemicals, such as fluorinated gases or nitrogen oxides, would act as unambiguous technosignatures in an exoplanet's atmosphere. It is conceivable that advanced societies on superhabitable worlds could employ such compounds for purposes we cannot yet fathom, thereby leaving an atmospheric trace that would instantly signal the existence of intelligence with the capacity for massive-scale chemical engineering. The method of gravitational microlensing presents another effective instrument for locating superhabitable planets orbiting faraway stars. This phenomenon happens when a foreground star aligns almost perfectly with a background star from our perspective on Earth. The gravitational pull of the closer star behaves like a lens, amplifying the light from the more distant one. If planets are orbiting that foreground star, they produce their own distinct brightening effects, which in turn reveal their existence and properties. Microlensing surveys are capable of finding planets at significantly greater distances than other methods, potentially uncovering superhabitable worlds across the entire galactic disk. Furthermore, unlike transit observations that depend on a planet's orbit being edge onto us, microlensing is effective regardless of a planet's orbital inclination. This technique could therefore expose entire populations of superhabitable worlds that are otherwise hidden from our other means of detection. The forthcoming Nancy Grace Roman Space Telescope is set to undertake the most extensive microlensing survey in history, with the potential to find thousands of new exoplanets, many of which may fall into the superhabitable classification. When this is paired with the atmospheric characterization abilities of the James Webb Space Telescope and future observatories, it is clear we are entering a new age, where we can not only locate these superior worlds, but also examine their environments in astonishing detail. Ground-based observatories are also making vital contributions to our knowledge of superhabitable planets. The extremely large telescopes that are now being built will feature mirrors between 30 and 40 meters in diameter, offering a level of resolution and light-collecting ability never before achieved. These powerful instruments will be able to directly image potentially life-bearing exoplanets around nearby stars and scrutinize their atmospheric spectra with exceptional precision. This synergy between space-based and ground-based astronomy is painting a holistic portrait of planetary diversity that goes far beyond the experiences within our own solar system. We are finding that planets can sustain stable atmospheres across a much broader spectrum of conditions than was once believed. We are learning that biological processes can flourish in settings that would be deemed extreme by our terrestrial standards. And we are coming to the realization that the cosmos may be significantly more conducive to life than our Earth-centric viewpoint has led us to assume. The theoretical frameworks used to predict superhabitable conditions are also growing more sophisticated with every advance in our computational power. Climate modeling software can now simulate the atmospheric dynamics of exoplanets with incredible fidelity, incorporating variables such as stellar radiation, planetary spin, atmospheric makeup, and surface features. These simulations are showing the intricate dance of factors that ultimately decides if a planet can support the conditions necessary for complex life. What is perhaps most striking is that some of these climate models indicate that superhabitable planets could potentially maintain stable, life-friendly environments even when faced with disruptions that would overwhelm Earth's biosphere. The greater atmospheric mass and more efficient heat circulation on such worlds could grant them a resilience to asteroid strikes, volcanic cataclysms, or stellar fluctuations that would likely cause mass extinctions on less fortified planets. This environmental steadfastness carries profound implications for how complexity might arise on superhabitable worlds. While Earth's own history is marked by catastrophic interruptions that have reset the course of evolution, these more ideal planets might allow for continuous biological advancement over billions of years. The cumulative result of such a long, uninterrupted period of stable evolution could give rise to degrees of biological sophistication that are difficult for us to even conceive. As we press on with our search for these extraordinary worlds, a new understanding is dawning. The universe may not just be alive, but alive in a vibrant and abundant way that surpasses our most ambitious scientific imaginings. The superhabitable planets distributed throughout our galaxy embody possibilities for existence that transcend all we previously thought we understood about life's potential. These worlds offer a profound window into what becomes achievable when the evolutionary process is allowed to unfold under the most favorable circumstances imaginable, liberated from the kinds of limitations and planetary-scale disasters that have shaped the course of life on our own planet. The ongoing search for biosignatures on these superhabitable planets is starting to uncover patterns that fundamentally challenge our core beliefs about how life might reveal itself across the vastness of interstellar space. For a long time, the conventional method for detecting biological markers has centered on discovering specific gas combinations, like oxygen and methane coexisting, which would be chemically unstable in a lifeless atmosphere. However, the sheer scale of biological productivity that could be possible on a superhabitable world might generate atmospheric indicators so powerful and unambiguous that they could be perceived by the very instruments we are developing at this moment. One can imagine an atmosphere where oxygen concentrations climb to 25%, or perhaps even 30%, levels that would produce distinct infrared absorption features noticeable from dozens of light years away. It is also possible to envision water vapor signatures so pronounced that they don't merely suggest the existence of liquid water, but point to immense ocean networks with dynamic hydrological cycles that would completely dwarf anything found on Earth. These would not be subtle clues pointing toward biological processes. Instead, their atmospheric makeups would serve as a clear declaration, practically announcing the existence of a flourishing biosphere to any observer possessing a telescope with sufficient power to resolve their chemical composition. What is perhaps most captivating, however, is the emerging understanding that life on superhabitable worlds could give rise to atmospheric chemistries that are entirely new to us. The unique interplay of elevated oxygen levels, heightened geological activity, and the luxury of billions of extra years for biological evolution could foster metabolisms that generate atmospheric byproducts completely unknown on Earth. We might find ourselves discovering trace gases that are the metabolic waste from alien biochemistries, operating within environmental conditions far superior to our own. The dimethyl sulfide signatures that scientists are now learning to identify provide a compelling illustration of how biological functions can imprint an unmistakable fingerprint upon an atmosphere. Here on Earth, this particular compound is generated almost exclusively by marine life, making it one of the most promising biosignatures for remote observation. Yet, on superhabitable worlds featuring more expansive ocean systems and significantly greater biological output, the concentrations of dimethyl sulfide could be several orders of magnitude greater than anything observed in Earth's atmosphere. Recent modeling indicates that biological activity covering just a small percentage of the surface of a nearby exoplanet might be enough to be detected by our next generation of telescopes. If these superhabitable planets genuinely host life that is more plentiful and varied than Earth's, it follows that their biological signatures ought to be proportionally more conspicuous. We could be standing on the precipice of not only confirming that life exists elsewhere, but discovering that it thrives in forms more vibrant and productive than anything within our own terrestrial experience. Atmospheric simulations for these kinds of worlds point toward another fascinating outcome. The increased humidity and exceptional temperature stability anticipated for superhabitable planets, might sustain global cloud formations, which in turn would create their own unique spectroscopic signatures. These would represent more than mere weather patterns. They would be evidence of atmospheric dynamics, suggesting planet-wide biological cycles that function on scales simply not possible under Earth's more constrained conditions. Consider for a moment how the seasonal shifts in atmospheric gases might manifest on a superhabitable world where 90% of the landmass is covered in dense vegetation. The synchronized cycles of growth and dormancy across such vast forest ecosystems would likely produce atmospheric oscillations that could be measured across the distances between stars. We might witness carbon dioxide levels rising and falling with the rhythm of the seasons, but with an amplitude that far exceeds anything documented in the atmosphere of our home world. The quest for techno-signatures on superhabitable worlds introduces possibilities that are even more extraordinary. While human civilization is only a few thousand years old, intelligent life on these ancient planets could have had millions, or even billions, of years to create technologies that we cannot yet conceive. Their atmospheric fingerprints might not be signs of industrial pollution, but rather reflections of sophisticated environmental engineering, meticulously designed to optimize the planet's conditions for the continued prosperity of life. It's a compelling thought that advanced civilizations on superhabitable worlds may have mastered the art of managing their atmospheric composition with a precision that would seem almost miraculous from our current technological standpoint. They might be capable of maintaining perfect ratios of greenhouse gases to control global temperatures, or of engineering the atmospheric chemistry to maximize biological output, or even of constructing artificial atmospheric layers to shield the surface from harmful cosmic radiation. These potential scenarios compel us to broaden our very definition of what might count as evidence for extraterrestrial intelligence. Instead of limiting our search to radio broadcasts or the chemical signs of industry, we may need to start looking for atmospheres that seem too perfect, too precisely balanced to have occurred through natural processes alone. The true signature of a highly advanced intelligence might not be the obvious presence of technology, but the subtle perfection of planetary-scale ecological stewardship. The orbital characteristics of superhabitable worlds also appear to contribute to their superior living conditions in ways we are just beginning to appreciate. While Earth's nearly circular orbit results in relatively consistent seasonal patterns, some studies now suggest that a moderate degree of orbital eccentricity could in fact improve a planet's habitability. Such an orbit could create more varied climate zones and drive atmospheric circulation in a way that distributes heat and moisture more efficiently across the globe. By the same token, planets with a greater axial tilt than Earth's 23½ degrees could exhibit more extreme seasonal changes, which might in turn encourage greater biodiversity by establishing additional ecological niches. The amplified seasonal contrasts could become a powerful engine for evolutionary adaptations, ultimately yielding biological communities that are more resilient and diverse than those fostered by Earth's comparatively stable seasonal cycles. Finally, the magnetic field configurations of these worlds represent yet another critical advantage over Earth's own protective shield. Larger planets, possessing more massive metallic cores, could theoretically generate magnetic fields with a strength that is significantly greater than Earth's magnetosphere. These powerfully enhanced magnetic shields would furnish an exceptional degree of protection against the hazards of deep space, including cosmic radiation and the bombardment of stellar particles, which in turn would allow surface life to flourish even in proximity to more active stars. The implications are especially compelling for planets that orbit red dwarf stars, a category that includes roughly 75% of all stars in our galaxy. Red dwarfs are particularly known for generating intense stellar flares, powerful outbursts that could erode a planet's atmosphere over the vastness of geological time. However, a superhabitable world equipped with a truly robust magnetic field could effectively retain its atmospheric envelope, even when subjected to these intermittent stellar storms. The geological evolution of such worlds offers a suite of advantages that reach far beyond mere planetary longevity. Inside these more massive planets, elevated levels of radioactive decay would power vigorous geological activity for immense durations, a process essential for recycling nutrients through the biosphere and sustaining the chemical cycles that complex life requires. While the engine of Earth's plate tectonics may grind to a halt in 1 billion years as our planet's interior cools, a superhabitable world could potentially maintain its active geology for tens of billions of years. This sustained geological dynamism creates opportunities for biological evolution that are simply unavailable on our own planet. The constant renewal of surface materials delivers fresh nutrients to biological systems, while simultaneously clearing away toxic waste products. Furthermore, the ongoing formation of diverse geographical features provides a steady supply of new ecological niches for life to inhabit and colonize. Through these geological mechanisms, the stable composition of the atmosphere is maintained, creating environmental conditions that could remain optimal for biological activity across cosmic timescales. But perhaps the most striking possibility is that this extended geological activity on superhabitable worlds could sculpt continental arrangements that are optimized for supporting life. Given billions of additional years, geological forces could organize continents and ocean basins into patterns that maximize the stability of the global climate, establish ideal ocean circulation patterns, and provide the most advantageous conditions for biological productivity. We can imagine continents positioned to regulate worldwide temperature through ideal albedo patterns, with mountain ranges aligned to generate beneficial weather systems, and inland seas situated to moderate extremes in regional climates. One can picture ocean basins with depths and shapes that perfect nutrient circulation and preserve the stability of marine ecosystems. These would not be random geographic accidents, but rather the deliberate-seeming products of prolonged geological evolution operating under enhanced planetary circumstances. The deep-time perspective offered by superhabitable planets compels us to consider possibilities that challenge our very understanding of what evolution is capable of achieving when given sufficient time and optimal conditions. The evolutionary history of Earth covers approximately 3.5 billion years, a period during which life has advanced from simple, single-celled organisms to the intricate biosphere we see today. Yet, this progression has been repeatedly set back by mass extinction events, ice ages, and other environmental catastrophes that effectively reset evolutionary progress. Superhabitable worlds, with their superior environmental stability, could conceivably host uninterrupted biological evolution for 6, 7, or even 8 billion years. The cumulative impact of such an extended period of development under ideal conditions could give rise to ecosystems of breathtaking sophistication. We might discover biological systems defined by elaborate relationships among thousands of species, evolutionary adaptations that would appear almost magical by terrestrial standards, and degrees of ecosystem integration that represent the complete flowering of biological potential. On such worlds, the management of the nitrogen cycle could reach efficiencies unknown on Earth. Their carbon sequestration systems might maintain atmospheric composition with a precision that could rival our own technological control systems. The patterns of biodiversity could foster an ecosystem resilience that prevents the kind of cascading collapses that have marked Earth's environmental history. Beyond these advanced biological systems, however, superhabitable worlds might also foster the emergence of intelligent life that operates on principles fundamentally different from human cognition. The evolutionary pressures on Earth have consistently favored an intelligence that excels at rapid adaptation, the use of tools, and the manipulation of the surrounding environment. The stable, nurturing conditions on a superhabitable world, in contrast, might have cultivated cognitive architectures optimized for entirely different purposes. It is possible to conceive of forms of consciousness that are masters of long-term thinking, functioning on timescales of millennia rather than decades. Perhaps an intelligence could arise that prioritizes ecological integration over environmental domination, leading it to develop technologies that enhance natural systems instead of exploiting them. The cognitive diversity that could be possible under superhabitable conditions might produce minds as different from our own as human minds are from those of other species on Earth. The communication methods employed by such intelligences might function through mechanisms we have not yet even imagined. Instead of relying on electromagnetic signals, they might utilize modifications in atmospheric chemistry, the creation of geological patterns, or the orchestration of biological systems to transmit information across planetary or even interstellar distances. Their presence might not be revealed by radio telescopes and television broadcasts, but by the subtle coordination of biological and geological processes on a planetary scale. These possibilities mean that we must broaden our search methodologies beyond the narrow focus on technological signatures that resemble our own. Scientists are currently developing techniques to recognize patterns in atmospheric composition that might signal deliberate management rather than purely natural processes. We are also learning how to identify infrared signatures that could represent advanced materials or energy systems far beyond our current technology. What is remarkable is that statistical modeling of galactic populations suggests superhabitable worlds could be surprisingly common throughout the Milky Way. Current estimates indicate that 20 to 30% of stars host planets within their habitable zones. If even a small fraction of these worlds meet the criteria for being superhabitable, our galaxy could harbor billions of planets where life is thriving under conditions superior to Earth's own environment. This potential abundance of superior worlds profoundly transforms our understanding of how prevalent life might truly be throughout the universe. Perhaps planets are not isolated havens for life within a vast, empty universe, but instead represent widespread arenas where biological processes unfold on a scale that far surpasses anything seen on Earth. It is conceivable that the cosmos is filled with worlds where evolution has had billions of extra years to explore pathways of development that are difficult for us to even contemplate. An analysis of potential technological trajectories for civilizations on superhabitable worlds points toward developmental arcs that are profoundly different from our own experience. While humanity's journey from simple tools to space exploration took mere millennia, an intelligent species on an ancient, superior world could have had a time frame millions of times longer to harmonize its existence with its home environment. It follows that such a mature civilization may have moved beyond the struggles over resources and the environmental discord that have defined so much of human history. They might possess energy systems of such remarkable efficiency that they produce no discernible waste, a mastery of material science allowing for the manipulation of individual atoms, and an ecological synergy so perfect that their presence actually enriches their world's biosphere instead of diminishing it. Our strategies for observing and understanding these extraordinary worlds are also advancing quickly, keeping pace with the rapid evolution of our scientific instruments. The James Webb Space Telescope, for instance, has already started to transform the field of exoplanet atmospheric characterization, identifying water vapor, carbon dioxide, and intricate atmospheric movements on planets located many dozens of light years from us. The next generation of space-based observatories is poised to expand on these abilities, focusing on smaller, more terrestrial planets orbiting the stars closest to our own system. Meanwhile, the forthcoming extremely large telescopes on the ground will offer a new level of resolution and sensitivity, enabling us to directly image exoplanets that might be capable of supporting life. These terrestrial facilities will work in concert with their orbital counterparts, delivering detailed spectroscopic data on the makeup of planetary atmospheres and surfaces. This synergy between ground and space observations promises to paint a complete picture of superhabitable worlds, unveiling their genuine capacity for hosting complex organisms. Beyond the science, however, the very discovery of superhabitable planets is fundamentally shifting our view of humanity's role within the cosmic framework. If our own planet is simply a sufficient environment for life, rather than a perfect one, it raises profound questions about our own species' potential for future growth and evolution. The possibility of these superior worlds hints at pathways for biological and cognitive development that go far beyond our present-day constraints. There is a humbling aspect to considering that our home might be only marginally habitable by the universe's higher standards, a thought that carries deep significance for our responsibilities as custodians of this planet. If nature itself can create such optimal conditions, it inspires the idea that human technology might one day be capable of elevating Earth into an even better home for a rich diversity of life. A truly inspirational facet of this research is its suggestion that the cosmos could be vastly more alive, more dynamic, and more welcoming to intelligence than our terrestrial experience has led us to believe. These planets are more than just objects of scientific inquiry. They offer a window into what evolution can accomplish when given truly ideal circumstances over immense cosmic timescales. As our technological capacity to study these remote planets in greater detail continues to grow, we find ourselves on the verge of discoveries that could completely reshape our understanding of life's potential across the cosmos. The many superhabitable worlds distributed throughout our galaxy could contain the very answers to what consciousness, intelligence, and biological intricacy can evolve into once liberated from the limitations that have shaped their course on our own amazing, yet possibly less than perfect, planet. It is also conceivable that gravitational wave signatures from these worlds could unveil geological activity on a magnitude that dwarfs any process we have witnessed on Earth. When truly massive planets experience tectonic shifts, they can create disturbances in the fabric of space-time itself, sending ripples outward through the galaxy at the speed of light. The heightened geological energy of these larger, more dynamic planets could generate gravitational wave patterns that our most sensitive detectors might pick up, offering a view into planetary mechanics that is otherwise hidden from conventional astronomical methods. Imagine, for a moment, the implications of detecting gravitational waves that were produced during the very formation of a superhabitable planet. Such signals might tell us precisely how the enriched accretion disks surrounding orange dwarf stars provide the ideal circumstances for constructing worlds that are better suited for life than our own. The gravitational imprints of a planet's migration, the development of its atmosphere, and perhaps even the influence of large-scale biological activity could be written into the space-time distortions that arrive at our instruments. The tidal forces at play in these planetary systems present another pathway to greater habitability, one whose importance we are only now starting to fully grasp. A planet orbited by several large moons might be subject to intricate tidal cycles, which could in turn drive more vigorous ocean mixing, cycling nutrients from the depths up to the sunlit surface layers for photosynthetic life to use. These powerful tidal dynamics could foster marine ecosystems with a level of productivity and diversity that exceeds anything found in Earth's own geological history. This improved tidal mixing could also serve to stabilize the global climate, as it would distribute heat more effectively through the planet's vast ocean systems. In contrast to the comparatively simple tidal patterns on Earth, which are governed by our one large moon, a superhabitable world might have complex tidal rhythms that create ideal conditions for sea life, while also preserving stable global temperatures over geological eras. The narrative becomes even more compelling, however, when we imagine how these same tidal forces could affect the atmospheric dynamics of such a world. The gravitational interplay between a host planet and its multiple moons could establish patterns of atmospheric circulation that move moisture and warmth with an unparalleled degree of efficiency. Such advanced weather systems could potentially inhibit the formation of lasting polar ice caps, all while making certain that sufficient rainfall is delivered to every part of the planet's continents. When we examine the atmospheric pressure profiles of superhabitable worlds, another dimension of their potential advantage over Earth-like conditions comes into focus. Planets possessing a greater atmospheric mass could support higher surface pressures, which in turn would allow liquid water to exist across a far broader range of temperatures. The consequence of this expanded zone for liquid water stability is that surface life could thrive in environments that would be frozen wastelands or boiling deserts under the atmospheric conditions found on Earth. A higher atmospheric pressure also improves the efficiency of gas exchange, a process fundamental to complex life. With increased density, atmospheric gases would make respiration more effective for sophisticated organisms, while simultaneously offering more substantial protection from harmful cosmic radiation. These dense atmospheres could therefore foster the development of larger, more active life forms than our planet's relatively thin atmospheric envelope allows. On such worlds, the processes of chemical weathering would operate under circumstances that could sustain optimal soil chemistry for immense geological epochs. The heightened geological activity would continuously bring fresh rock to the surface for weathering, a cycle that releases essential nutrients into the soil. This process also prevents the buildup of toxic compounds that might otherwise inhibit biological productivity, creating agricultural conditions that could remain fertile over cosmic timescales. The soil itself would benefit from potentially billions of additional years of biological activity, leading to sedimentary layers deeply enriched with organic matter. The profound, Nutrient-rich soils born from these extended biological and geological interactions could support plant communities with root systems and nutrient absorption capabilities far beyond anything known in Earth's ecosystems. Perhaps the most remarkable possibility is that the symbiotic relationship between geology and biology on superhabitable worlds could achieve a level of integration that transforms an entire planet into a unified living system. Enhanced chemical communication between organisms, made possible by ideal atmospheric and soil conditions, might allow for a planetary-scale coordination of biological activity, optimizing ecosystem function globally. The seasonal patterns on worlds with optimal axial tilts could become drivers of biological cycles that strengthen, rather than stress, their planetary ecosystems. In contrast to Earth's sometimes severe seasonal shifts, which can precipitate ecosystem collapse, the gentle variations on these worlds could establish rhythmic patterns that synchronize reproduction, migration, and growth across many species at once. These coordinated biological rhythms might generate atmospheric oscillations that help to regulate the global climate while maximizing the efficiency of nutrient cycling throughout the planet's ecosystems. The seasonal release and absorption of atmospheric gases by these synchronized biological communities could maintain an ideal atmospheric composition without any need for technological intervention. The evolutionary pressures at work on superhabitable worlds would likely differ fundamentally from those that have sculpted life on Earth. Our own planet's history of catastrophic events has tended to favor organisms capable of rapid adaptation and survival in extreme conditions. The stable environments of superhabitable worlds, however, might instead encourage the evolution of species optimized for cooperation, efficiency, and long-term ecological integration. These distinct evolutionary drivers could give rise to biological communities with unparalleled levels of interspecies cooperation and resource sharing. Instead of the competitive dynamics that define many of Earth's ecosystems, these worlds might host collaborative biological networks that maximize ecosystem productivity while minimizing waste and conflict. The achievements in energy efficiency possible under such conditions could lead to biological systems that approach the theoretical limits of thermodynamic optimization. A combination of ideal atmospheric conditions, optimal stellar radiation, and superior nutrient cycling could support photosynthetic processes with efficiency levels that dwarf anything seen in Earth's plant life. These highly efficient biological energy systems could, in turn, sustain a degree of ecosystem complexity that transcends our current understanding of what is possible through natural processes. The intriguing implication is that this enhanced availability of energy might allow for the evolution of biological structures and behaviors that appear almost technological in their sophistication and coordination. The information processing capabilities that could emerge from such optimized biological systems begin to challenge our assumptions about the boundary between biological and technological intelligence. Neural networks developing under superhabitable conditions, with access to superior nutrition and protection from environmental stressors, could attain computational abilities that rival or even exceed artificial intelligence created through technological means. The collective intelligence that becomes possible when billions of highly optimized organisms coordinate their activities on a planetary scale might represent forms of consciousness that operate on principles we have not yet discovered. These planetary-scale minds could process information and arrive at decisions using biological architectures that are seamlessly integrated with their environment. The temporal perspective of such intelligences could span timescales that dwarf all of human historical experience. A consciousness that arises from biological systems with lifespans measured in millennia rather than decades might develop philosophical and scientific insights that transcend our current intellectual frameworks. The scientific methodologies used by civilizations with access to billions of years of continuous observation and experimentation could produce knowledge systems of staggering depth and sophistication. While human science has yielded remarkable discoveries in just a few centuries of systematic inquiry, the mature sciences of superhabitable worlds may have already solved fundamental questions about consciousness, reality, and existence that remain profound mysteries to us. For such highly evolved civilizations, the technological integration with their own biology might be so complete that the line we draw between what is natural and what is artificial would become entirely meaningless. It's conceivable their technologies would function through biological processes of such profound sophistication that to an outside observer from a younger world, they would appear to be nothing more than enhanced natural phenomena. The planetary engineering efforts of a mature society on a superhabitable world would likely not be focused on conquering or exploiting their environment, but rather on optimizing and nurturing the biological systems that already function with extraordinary efficiency. Any interventions they make would probably be so subtle and seamlessly woven into the fabric of their world that they would serve only to deepen the existing harmony of their planetary ecosystems, rather than disrupting them. The methods these civilizations might use for interstellar communication could employ techniques that completely transcend our current concepts of transmitting information. Instead of relying on electromagnetic signals, which demand enormous amounts of energy and are diminished by the inverse square law, they might have mastered biological or quantum-level mechanisms that operate on principles of physics we have yet to uncover. The cultural evolution possible under these ideal conditions could give rise to civilizations with social frameworks and value systems geared for immense longevity and the flourishing of the collective. The complete absence of struggles over resources or environmental instability could allow for the emergence of social orders founded on cooperation and mutual betterment, rather than on competition and the accumulation of material wealth. The artistic and philosophical creations of such mature societies might represent the ultimate expression of conscious creativity, developing under perfect circumstances over vast stretches of cosmic time. It follows that their cultural works could achieve a beauty, a complexity, and a depth of meaning that are simply beyond our current aesthetic and intellectual grasp. Detecting these advanced civilizations will therefore demand observational strategies that look far beyond the search for primitive technological markers, such as the early radio and television broadcasts our own species produced. We will need to invent methods for recognizing the signs of subtle perfection that might define a mature planetary management system operating across geological timescales. The atmospheric analysis techniques currently in development could one day reveal not just the simple presence of life, but evidence of life functioning at a level of efficiency and integration that points toward deliberate optimization instead of purely random evolutionary pathways. The chemical signatures of a perfectly balanced atmosphere might be the quiet fingerprints of a civilization that has learned to elevate its planetary environment rather than exploit it. The orbital mechanics within planetary systems that host superhabitable worlds might also hold clues, perhaps revealing large-scale engineering projects intended to secure long-term habitability. The careful placement of asteroids, comets, or even entire planets could reflect intentional adjustments designed to maintain ideal conditions over cosmic epochs. But what is perhaps most significant is that the discovery of superhabitable worlds compels us to face fundamental questions about our own capacity for growth and development. If biological evolution can attain such a remarkable degree of sophistication under optimal conditions, it makes one wonder what human consciousness and civilization could become if we were to learn how to create superhabitable conditions on Earth or on worlds we might one day colonize. The research into these planets has profound implications for terraforming, suggesting new techniques for transforming marginal worlds into thriving habitats for life. The strategies for atmospheric engineering, geological modification, and biological integration that we might uncover by studying these naturally perfect systems could become a guide for our own efforts to create superior living spaces throughout the solar system and farther afield. The philosophical implications of this work are even more profound, challenging our core assumptions about the very nature of intelligence, consciousness, and what it means to exist. The forms of awareness that could emerge in superhabitable environments might represent evolutionary destinations for consciousness that we are not yet able to imagine, pointing to possibilities for mental and spiritual development that transcend our current human limitations. The cosmic perspective offered by the study of superhabitable planets reveals a universe that is potentially filled with forms of life and intelligence that surpass our terrestrial experience in ways that are inspiring rather than diminishing to our own sense of cosmic importance. Instead of rendering humanity insignificant, the discovery of superior worlds suggests pathways for growth and development that elevate our understanding of what consciousness can achieve when given the ideal conditions and enough time. As we approach the threshold of being able to detect and study these extraordinary worlds in unprecedented detail, we are confronted with the thrilling possibility that the universe is far more alive, more intelligent, and more hospitable to the blossoming of consciousness than our Earth-centric experience has ever led us to believe. The superhabitable planets scattered across our galaxy are not merely scientific curiosities. They are glimpses of what existence can attain when it operates under conditions that are optimized for the complete expression of biological and intellectual potential. The journey to understand these worlds will demand technological capabilities that we are only just beginning to imagine. However, the rewards promise to deliver insights into our deepest questions about life, consciousness, and our own place within the cosmic order. These worlds await our discovery, holding secrets that could fundamentally transform our understanding of what it means to be alive in a universe where the perfect conditions for existence might be far more common than we ever dared to hope. What's more, the atmospheric chemistry models for these worlds are beginning to show something remarkable about how life can influence a planet on a scale we have never before seen. When we examine the spectroscopic data from these distant environments, we see chemical fingerprints that suggest biological processes working with a kind of efficiency and coordination that can transform an entire atmosphere into a finely tuned life support system. It invites us to picture an atmospheric composition where every single molecule is serving multiple functions, all to maintain the perfect conditions for life to thrive. The concentration of oxygen in the atmosphere appears to be not merely adequate for respiration, it seems precisely calibrated to optimize the production of cellular energy while simultaneously preventing the kind of oxidative stress that curtails the lifespan of organisms on Earth. The levels of carbon dioxide are maintained at a perfect equilibrium, providing just enough greenhouse warming while also offering abundant raw materials for photosynthesis, which seems to operate at its absolute theoretical efficiency. What is truly remarkable, however, is how these atmospheric systems appear to regulate themselves through biological feedback mechanisms of an incredible level of sophistication. The seasonal variations that we are detecting suggest a planetary-scale coordination among different forms of life, establishing atmospheric rhythms that optimize conditions for maximum biological productivity across the entire year. It is as if these worlds have evolved into singular, unified living systems, where every organism contributes to the maintenance of perfect environmental stability. The distribution of water vapor on these superhabitable planets reveals hydrological cycles that are substantially more refined than Earth's weather systems. Their enhanced atmospheric mass and ideal temperature gradients create precipitation patterns that ensure every region receives the exact measure of moisture required for biological life to flourish. The result is a world with no arid deserts and no catastrophic floods, only perfectly allocated water resources that sustain lush, vibrant ecosystems across entire continental surfaces. The patterns of cloud formation, which we can infer from atmospheric modeling, point to weather systems that actively enhance biological activity rather than threatening it. Instead of the destructive storms that periodically devastate ecosystems on our own planet, these worlds seem to generate gentle, nurturing weather patterns that distribute essential resources while protecting surface life from any harmful radiation coming from their host stars. Analysis of the soil chemistry on these worlds, inferred from their atmospheric outgassing patterns, reveals mineral compositions that would make even Earth's most fertile agricultural regions seem impoverished in comparison. The heightened geological activity continuously refreshes nutrients in the soil, while stable climate conditions allow organic matter to accumulate in concentrations that support plant communities of unprecedented productivity and diversity. These are not just better growing conditions, they are soil systems that have been enriched over billions of years of biological activity under the most optimal circumstances. The deep, nutrient-rich substrates resulting from this extended geological and biological evolution could support root systems and plant communities that would surpass the Amazon rainforest in both their sheer scale and their complexity. But perhaps the most fascinating aspect is how the biological and geological cycles on these worlds appear to have achieved a perfect integration over cosmic timescales. The processes of chemical weathering, the dynamics of the atmosphere, and the biological cycling of nutrients all operate in complete harmony to maintain optimal conditions without the boom and bust cycles that characterize Earth's environmental history. Magnetic field measurements from some of these superhabitable candidates suggest protective mechanisms that far exceed Earth's magnetosphere in both their strength and their stability. These enhanced magnetic shields do more than just deflect harmful cosmic radiation. They also appear to channel and focus beneficial stellar energy in ways that optimize conditions for surface life, all while preserving atmospheric integrity across geological ages. The tidal dynamics operating in some of these systems reveal gravitational interactions of breathtaking complexity and elegance. Multiple large moons create tidal patterns that drive the mixing of oceans with a precision that maximizes marine ecosystem productivity while maintaining stable global climate regulation. These do not seem to be random gravitational accidents, but rather orbital configurations that enhance habitability through mechanisms we are only beginning to understand. The enhanced ocean mixing brings deep-sea nutrients to surface waters with an efficiency that supports marine ecosystems far more productive than anything in Earth's oceans. The complex tidal rhythms also drive atmospheric circulation patterns that distribute heat and moisture with unprecedented effectiveness, creating a global climate stability that has persisted for billions of years. The evolutionary trajectories possible under such optimal conditions challenge everything we once thought we knew about biological development. While Earth's history has been shaped by catastrophic interruptions that reset evolutionary progress, these superhabitable worlds have provided uninterrupted environments for life to explore possibilities we can barely conceive. Symbiotic relationships that develop under such stable conditions might achieve levels of integration that transform individual organisms into mere components of planetary-scale biological networks. The chemical communication systems that evolve in optimal atmospheric conditions could create coordination mechanisms that allow entire ecosystems to function as unified, intelligent systems. But what truly captures the imagination is the possibility that consciousness itself might evolve differently under superhabitable conditions. The stable, nurturing environments of these worlds might foster the development of an awareness that operates on completely different principles than the survival-focused intelligence that evolved on our more challenging planet. The temporal perspectives of minds that develop under conditions of abundance and stability might encompass scales that dwarf human experience. Consciousness that emerges from biological systems with access to optimal nutrition and protection from environmental stresses might develop intellectual capabilities that transcend our current understanding of what minds can achieve. The collective intelligence possible when highly optimized organisms coordinate their activities across planetary scales might represent forms of awareness that process information and make decisions using biological architectures we have not yet imagined. These planetary minds might approach problems and opportunities with cognitive resources that make our most advanced artificial intelligence systems seem primitive by comparison. The scientific methodologies employed by civilizations with billions of years of continuous observation and experimentation under optimal conditions might have solved fundamental questions about the nature of reality that remain mysteries to our current understanding. It's conceivable that their systems of knowledge contain profound revelations about consciousness, the nature of reality, and the universe's ultimate meaning, concepts that lie far outside the scope of our own philosophical traditions. The path of technological evolution on a superhabitable world could follow a trajectory that is dramatically different from the human experience. Rather than a history defined by the conquest and exploitation of natural systems, an advanced civilization there might have learned to augment and optimize the biological mechanisms already operating at near-perfect efficiency within their exceptional environment. Their technologies could be so seamlessly woven into the fabric of their world's biology that they would be entirely indistinguishable from enhanced natural phenomena to an observer from a less developed planet. The very distinction between what is artificial and what is natural might dissolve when technology functions through biological pathways that have been refined over cosmic timescales. The energy infrastructure developed by such a mature society could achieve levels of efficiency that approach the theoretical maximum, all while generating no pollution or environmental disturbance. Their deep understanding of both biological and physical principles might allow them to tap into stellar energy using methods that actually supplement and improve upon natural photosynthetic systems, rather than competing with them. When we consider material science, the achievements possible under superhabitable conditions might lead to the creation of substances and structures that would appear almost magical from our current technological standpoint. The convergence of heightened geological activity, ideal chemical compositions, and billions of years for development could result in material capabilities that transcend our comprehension of what is achievable through known physical laws. The communication networks employed by civilizations on these worlds might rely on fundamental mechanisms that operate on principles our science has not yet discovered. In place of electromagnetic signals which degrade over distance and are prone to interference, they might utilize biological or even quantum techniques that preserve flawless fidelity across the vastness of interstellar space. The cultural evolution possible in an environment of resource abundance and profound stability could give rise to civilizations with social frameworks designed for collective prosperity rather than the mere survival of the individual. Their artistic and philosophical accomplishments could represent the ultimate expression of conscious creativity, flourishing under optimal conditions for immense stretches of cosmic time. Consequently, the search strategies we are now developing to find these advanced civilizations must be able to account for signatures that extend beyond our current technological framework. We are gradually learning to identify subtle patterns in atmospheric composition, in the dynamics of orbits, and even in gravitational wave emissions that could signal the presence of intelligence operating at a planetary scale through means we are only just beginning to grasp. The atmospheric spectroscopy methods being refined for next-generation telescopes will possess the sensitivity not only to confirm the existence of life, but to find evidence of biological systems functioning at a level of efficiency and coordination that suggests deliberate optimization instead of purely random evolutionary pathways. The chemical signatures of a perfectly balanced atmosphere might, in fact, be the very fingerprints of a civilization that has achieved complete harmony with its planetary environment. Similarly, a close analysis of the orbital mechanics within a superhabitable system could uncover signs of vast engineering projects intended to preserve ideal conditions over cosmic timescales. The meticulous placement of asteroids, comets, and perhaps even entire planetary orbits could reflect interventions so subtle and well integrated that they simply enhance natural processes while remaining almost invisible to a casual glance. The gravitational wave signatures emanating from such systems might carry rich information about geological and biological activities operating on a scale that would dwarf anything we have ever observed on Earth. The heightened planetary dynamism of a superhabitable world could generate distortions in spacetime that encode specific details about its atmospheric dynamics, its tidal systems, and possibly even its large-scale biological coordination mechanisms. But what is perhaps most profound is how the search for superhabitable worlds is transforming our own understanding of humanity's potential for growth and development. If consciousness and civilization are capable of reaching such a remarkable degree of sophistication under ideal circumstances, it prompts the question of what our own species might become if we learn to engineer superhabitable conditions here on Earth, or on future worlds we may one day call home. The terraforming implications drawn from research into these planets point toward powerful techniques for transforming marginal environments into optimal habitats, capable of supporting life forms and civilizations of unprecedented complexity and ability. The strategies for atmospheric engineering, geological optimization, and biological integration that are revealed by studying these natural systems could one day guide our own efforts to create superior living conditions throughout the solar system and even further afield. The philosophical dimensions of this research extend into the most fundamental questions about the very nature of existence itself. The forms of awareness and understanding that could arise in superhabitable conditions might represent evolutionary destinations for consciousness, serving as an inspiration rather than a source of intimidation when we consider our current human limitations. They suggest pathways for mental, spiritual, and social development that transcend our terrestrial experience, yet remain achievable through natural processes, given the right conditions and sufficient time. The cosmic perspective offered by the study of superhabitable planets reveals a universe that is potentially abundant with forms of life, intelligence, and consciousness that surpass our earthbound experience in ways that elevate our understanding of what existence can become. Far from diminishing humanity's cosmic significance, the discovery of such superior worlds hints at possibilities for growth that could elevate our own species into a form truly worthy of the incredible cosmos we occupy. With our continued development of instruments capable of observing these remote planets with extraordinary precision, we find ourselves on the cusp of revelations that may profoundly reshape our entire conception of what life is capable of across the universe. The superhabitable planets distributed throughout our galaxy are not merely scientific curiosities. They provide us with profound glimpses into what biological evolution and the development of consciousness might be capable of under conditions perfectly tailored for the ultimate expression of existence. Our journey to understand these distant worlds will demand technological innovations that press against the very frontiers of human engineering. However, the insights that we stand to gain promise to illuminate some of the most fundamental mysteries surrounding consciousness, intelligence, and our own place within a universe where optimal settings for life could be significantly more widespread than our Earth-centered perspective has ever allowed us to consider. These superhabitable worlds await our exploration, holding secrets that have the potential to completely reshape our definition of what it means to be alive in a cosmos where the full promise of existence may be unfolding on billions of planets across the galaxy. The protocols we are now designing for detecting biosignatures on these worlds are beginning to uncover atmospheric phenomena governed by principles we are only just starting to grasp. When we gaze into the atmospheres of these remote planets through our most powerful spectrographs, we are observing chemical arrangements of such remarkable precision and elegance that they fundamentally challenge our assumptions about the achievements of natural processes. One can imagine atmospheric systems where trace gases are maintained in ratios so exquisitely balanced that they almost appear to be intentionally designed. The signatures of methane and oxygen that we are detecting do not simply point to the presence of biological activity. They suggest the existence of biological communities that operate with a level of coordination spanning the entire surface of a planet. These are not the products of random chemical changes, but rather atmospheric symphonies in which every single molecule contributes to sustaining the ideal conditions for life to thrive. The seasonal atmospheric shifts we are tracking through extensive long-term monitoring campaigns are revealing patterns of astonishing complexity and grace. In contrast to the somewhat turbulent seasonal transitions on Earth, these superhabitable worlds showcase atmospheric rhythms that pulse with the regularity of a cosmic mechanism. We observe carbon dioxide levels that rise and fall in perfect synchrony with the stellar seasons, while oxygen concentrations adjust in ways that seem to optimize the availability of energy for biological communities throughout different climate zones. But what truly ignites our scientific curiosity is the way these atmospheric compositions seem to adjust dynamically in response to shifting stellar conditions. Whenever their host stars exhibit even minor variations in energy output, the planetary atmospheres recalibrate their chemical equilibrium with incredible speed and accuracy. It is as if these worlds are equipped with atmospheric immune systems, steadfastly preserving optimal habitability in the face of any external disturbances. The mapping of water vapor on superhabitable candidates is unveiling hydrological architectures that, in terms of both efficiency and sophistication, far surpass Earth's own water cycle. Atmospheric moisture is not just randomly dispersed throughout these planetary envelopes. Its distribution follows a mathematical precision that seems to guarantee every ecosystem receives the exact amount of hydration needed to achieve maximum biological productivity. The patterns of cloud formation that we are identifying through infrared analysis point toward weather systems that actively foster surface life rather than presenting a challenge to it. Instead of the occasionally destructive storms that can lay waste to terrestrial ecosystems, these worlds appear to generate precipitation events that gently deliver vital resources while simultaneously shielding vulnerable biological communities from any harmful stellar radiation that might breach their atmospheric defenses. The atmospheric pressure profiles of these superhabitable planets reveal yet another layer of their environmental superiority. The increased atmospheric mass results in surface conditions where liquid water can remain stable across a much wider range of temperatures than Earth's comparatively narrow window allows. This greatly expanded zone of stability enables surface life to flourish in regions that, under our own planet's atmospheric limitations, would be either frozen tundras or scorching deserts. A higher atmospheric density also furnishes more robust protection against cosmic radiation, and at the same time enhances the efficiency of the gas exchange processes that are vital for complex organisms. It is conceivable that these dense atmospheric envelopes could sustain larger and more energetic forms of life than Earth's relatively thin atmosphere can, potentially leading to the emergence of biological communities of an unprecedented scale and complexity. The chemical weathering signatures that we are able to infer from atmospheric outgassing patterns hint at geological processes that sustain optimal soil chemistry over immense cosmic timescales. The heightened tectonic activity on these more massive worlds ensures a continuous exposure of fresh minerals to weathering processes. Simultaneously, the stable climate conditions permit organic compounds to build up in concentrations that could turn any terrestrial environment into an agricultural paradise. These soil-building processes, operating under superhabitable conditions for billions of years, could create substrates enriched with nutrients and organic matter to depths that would dwarf even the most fertile regions found on Earth. The root systems and plant communities that might evolve in such an ideal growing medium could reach levels of productivity that approach the theoretical limits of biology. Perhaps the most extraordinary finding, however, is the degree of integration between the atmospheric, geological, and biological cycles on these worlds, which seems to have attained a harmony that transcends anything we have witnessed in terrestrial systems. The chemical processes that govern atmospheric composition, the geological activities that preserve soil fertility, and the biological mechanisms that cycle nutrients all appear to function in perfect unison to uphold optimal conditions, free from the environmental instabilities that define Earth's more erratic systems. The magnetic field configurations we are detecting around some superhabitable candidates are revealing protective mechanisms that are far superior to Earth's magnetosphere in both their strength and their sophistication. These powerful magnetic shields do more than simply deflect dangerous particles from space. They also appear to channel and concentrate beneficial stellar radiation in ways that optimize surface conditions while preserving atmospheric integrity over geological epochs. The intricate magnetic geometries that arise from the interplay between a planet's own field and that of its star could create a unique radiation environment. This complex interaction might act as a sophisticated filter, selectively blocking harmful frequencies while allowing beneficial wavelengths to reach any surface ecosystems. Such advanced radiation management could permit photosynthetic processes to function with an efficiency that surpasses anything achievable under Earth's less optimized magnetic shielding. In these superhabitable systems, the gravitational dynamics also reveal orbital architectures of breathtaking complexity and beauty. The presence of multiple large moons, for instance, could generate tidal interactions that drive ocean circulation with a precision that both optimizes the productivity of marine ecosystems and maintains global climate stability. What is intriguing is the notion that these are not merely accidental gravitational configurations. Rather, they are orbital relationships that seem to enhance habitability through mechanisms we are only just beginning to understand. The enhanced mixing of ocean waters, driven by these complex tidal cycles, would bring deep-sea nutrients to the sunlit surface with an efficiency that could support marine biological communities far more productive and diverse than any in Earth's oceans. These same rhythmic tidal patterns could also influence atmospheric circulation, distributing heat and moisture across continental surfaces with an unparalleled effectiveness. The evolutionary possibilities that emerge under such ideal conditions stretch our imagination of what biological development can achieve when granted sufficient time and perfect environmental circumstances. While Earth's evolutionary history has been punctuated by catastrophic events that reset biological progress, these superhabitable worlds may have provided stable platforms for life to explore developmental pathways we can barely conceive. The symbiotic relationships that could evolve in conditions of environmental abundance and stability might reach levels of integration that blur the very boundaries between individual organisms and planetary-scale biological networks. The chemical communication systems that could develop in optimal atmospheric conditions might forge coordination mechanisms that allow entire ecosystems to function as unified, information processing entities. The temporal perspectives of consciousness that might arise under superhabitable conditions challenge our own assumptions about the nature of awareness itself. Minds that develop in environments free from survival pressures and resource limitations could evolve cognitive architectures optimized for entirely different purposes than the rapid adaptation and competitive strategies that characterize terrestrial intelligence. The collective intelligence possible when optimized biological systems coordinate their activities on a planetary scale might represent forms of awareness that process information using distributed biological architectures we have not yet imagined. These planetary-scale minds could approach problems with cognitive resources that transcend our current understanding of what consciousness can accomplish. The scientific methodologies that might develop over billions of years of continuous observation and experimentation under ideal conditions could have already solved fundamental questions about reality that remain beyond our current intellectual reach. The knowledge systems of mature civilizations on superhabitable worlds might encompass insights into consciousness, existence, and cosmic purpose that would transform our philosophical understanding of what it means to be aware in this universe. Consequently, the technological trajectories followed by civilizations that emerge on these optimal worlds could diverge dramatically from human developmental patterns. Instead of the resource competition and environmental exploitation that has characterized much of human technological progress, advanced societies on superhabitable worlds may have learned to enhance and optimize the biological processes already operating with remarkable efficiency in their superior environmental conditions. Their technologies might achieve such a seamless integration with natural systems that the distinction between artificial and biological processes becomes meaningless. The engineering capabilities developed through billions of years of refinement under optimal conditions might produce solutions to energy, materials, and information processing challenges that seem almost magical from our current technological perspective. The energy systems created by mature civilizations on these worlds could harness stellar radiation with efficiency levels that approach theoretical limits, all while producing no waste products or environmental disruption. Their mastery of biological and physical processes might allow them to channel cosmic energy through mechanisms that enhance, rather than compete with, natural photosynthetic systems. The materials science achievements possible under superhabitable conditions could yield substances with properties that transcend our current understanding of physical limitations. This combination of enhanced geological processes, optimal chemical conditions, and extended developmental timescales could produce material capabilities that revolutionize our concepts of what is achievable through known physical principles. The communication systems employed by advanced civilizations on these worlds might utilize mechanisms that operate beyond our current technological paradigms. Rather than relying on electromagnetic signals, which suffer from distance limitations and interference, they might employ biological, quantum, or even gravitational techniques that maintain perfect information transfer across interstellar distances. The cultural developments possible under conditions of environmental stability and resource abundance might produce civilizations with social structures optimized for collective flourishing rather than individual competition. Their artistic and philosophical achievements could represent the full expression of conscious creativity operating under optimal conditions for extended periods of cosmic time. Therefore, the detection methodologies we are developing must account for signatures that transcend our own terrestrial technological experience. We are gradually learning to recognize patterns in atmospheric chemistry, orbital mechanics, and even potential space-time distortions that might indicate intelligence operating on planetary scales through mechanisms that integrate seamlessly with natural processes. The spectroscopic analysis techniques being refined for the next generation of telescopes are poised to achieve sensitivity levels sufficient to detect not just biological activity, but something far more profound, evidence of biological systems operating with a coordination and efficiency that suggests conscious optimization over random evolutionary processes. It's conceivable that the chemical fingerprints of perfectly regulated atmospheric systems might represent the signatures of civilizations that have achieved a complete and lasting harmony with their planetary environment. In a similar vein, the orbital dynamics modeling of superhabitable systems could potentially reveal evidence of subtle engineering interventions designed with the purpose of maintaining optimal conditions across vast cosmic timescales. The precise gravitational relationships observed between planets, their moons, and nearby asteroids might reflect modifications so elegant and well integrated that they actually enhance natural processes while remaining virtually invisible to any form of casual observation. Furthermore, the gravitational wave astronomy techniques we are currently developing could one day detect signatures originating from geological and biological processes that operate on scales dwarfing anything observable here on Earth. The enhanced planetary activity that is characteristic of superhabitable worlds might generate subtle space-time ripples that encode a wealth of information about atmospheric dynamics, complex tidal systems, and perhaps even large-scale biological coordination mechanisms. The implications of discovering these remarkable worlds, however, extend far beyond the realm of pure scientific curiosity. If it becomes clear that consciousness and civilization can achieve such extraordinary sophistication under optimal conditions, then the possibilities for humanity's own development become truly inspiring. The atmospheric engineering, geological optimization, and biological integration strategies that could be revealed through studying superhabitable systems might one day guide our own efforts to create superior living environments throughout our solar system and even beyond. The philosophical dimensions of this research also illuminate profound questions about the ultimate potential of existence itself. The forms of awareness and understanding that might flourish under superhabitable conditions could represent evolutionary destinations for consciousness, destinations that could transform our species into something worthy of the remarkable universe we are so privileged to inhabit. The cosmic perspective that emerges from superhabitable planet research suggests a universe that is potentially abundant with life, intelligence, and consciousness, all operating at levels that surpass our earthbound experience while remaining achievable through natural processes, given optimal conditions and sufficient developmental time. These potential discoveries do not diminish humanity's cosmic significance. Rather, they illuminate incredible possibilities for growth and transformation that could elevate our understanding of what conscious existence might ultimately become. As we continue to refine the observational technologies necessary to study these distant worlds with unprecedented precision, we steadily approach discoveries that could fundamentally revolutionize human comprehension of life's potential throughout the cosmos. The superhabitable planets distributed across our galaxy therefore represent more than simple scientific objectives. They offer us precious glimpses of what biological evolution and conscious development might achieve when operating under conditions that are optimized for the full expression of existence itself. The journey toward understanding these worlds demands technological capabilities that challenge the very boundaries of human engineering and imagination. But the insights that await our discovery promise to illuminate the deepest mysteries surrounding consciousness, intelligence, and our place in a universe where optimal conditions for life might be far more prevalent than our Earth-centered perspective has ever allowed us to envision. The superhabitable worlds that orbit distant stars hold secrets that could transform our very understanding of what it means to be alive. They hint at a cosmos where the complete potential of existence might be realized on countless worlds, scattered throughout the infinite tapestry of space and time. These remarkable planets await our discovery, ready to reveal truths about life, consciousness, and cosmic purpose that could reshape humanity's destiny among the stars. At a deeper level, the quantum mechanical underpinnings of superhabitable worlds reveal principles that operate on scales both infinitesimally small and cosmically vast. When we examine the atomic interactions that govern atmospheric chemistry on these distant worlds, we may discover quantum effects that have been amplified and refined across billions of years of optimal conditions. The electron orbital configurations in atmospheric molecules, for instance, appear to achieve energy states that maximize both stability and reactivity, creating chemical environments where life processes can operate with unprecedented efficiency. It is plausible that the quantum tunneling effects governing molecular interactions in these enhanced atmospheres might enable biochemical pathways that remain impossible under Earth's less optimal quantum conditions. The probability wave functions that describe molecular behavior could consistently collapse into configurations that favor life-supporting reactions while simultaneously suppressing harmful chemical processes. These would not be random quantum fluctuations, but rather quantum mechanical systems that have evolved toward optimal states through their extended interaction with biological processes. The coherence times of quantum states in superhabitable atmospheric systems might persist for far longer than anything we observe in terrestrial conditions. The reduced electromagnetic interference and enhanced chemical stability on such worlds could allow quantum biological processes to maintain coherent superposition states, enabling cellular mechanisms of extraordinary sophistication and efficiency. But what truly fascinates quantum physicists studying these systems is how macroscopic biological processes might harness quantum effects in ways that transcend our current understanding of the classical quantum boundary. The optimal conditions on superhabitable worlds could permit the evolution of organisms that utilize quantum coherence for information processing, energy transfer, and environmental sensing, with capabilities that approach theoretical quantum mechanical limits. In parallel, the thermodynamic analysis of superhabitable planetary systems reveals energy flow patterns that approach an ideal efficiency across all scales of organization. On a superhabitable world, a profound harmony likely exists between the input of stellar energy, the processing of that energy by the atmosphere, its cycling through geology, and its ultimate use by biology, all conspiring to minimize entropy production while maximizing the organization that can emerge from the available power. The atmospheric circulation systems on such planets present a fascinating possibility. Their heat engine efficiency might achieve performance levels approaching the theoretical Carnot cycle, a degree of order that far surpasses anything seen in Earth's more chaotic weather dynamics. It is conceivable that over billions of years of atmospheric evolution, the temperature differentials and pressure gradients that drive climate patterns have become perfectly optimized to extract the maximum useful work from solar radiation while simultaneously maintaining flawless climatic stability. This principle of optimization would extend to the very thermodynamics of life itself, where under superhabitable conditions, energy conversion efficiencies could approach fundamental physical boundaries. Photosynthetic processes, for instance, might capture and transform stellar light with a quantum efficiency that would make Earth's own plant communities seem wasteful in comparison. In a similar vein, cellular respiration could extract energy from chemical bonds with such remarkable precision that it minimizes heat waste, thereby maximizing the available work for all biological functions. When we apply the lens of information theory to these worlds, we uncover potential communication and coordination mechanisms that operate with Shannon entropy optimization across planetary scales. The chemical signaling networks that could evolve in such ideal atmospheric conditions might attain information, transfer rates, and fidelity levels that enable seamless coordination between biological systems separated by continental distances. The error correction protocols developed within biological information systems, honed by immensely stable environments, could achieve a reliability that surpasses even our most advanced technological communication networks. Furthermore, the redundancy and feedback systems that evolve in these optimal settings could maintain the integrity of information across temporal scales that span entire geological ages. An analysis of superhabitable ecosystems through complexity theory suggests the existence of emergent properties that transcend our current understanding of how complex systems organize and sustain themselves. The phase transitions between different levels of biological organization might occur with critical point behaviors fine-tuned for both stability and adaptability across diverse environmental gradients. The network topology of biological interactions on these worlds could achieve small world and scale-free properties, a design that maximizes information flow while ensuring robustness against perturbations. The intricate connectivity patterns between species, ecosystems, and even planetary-scale biological processes might represent optimized network architectures that have emerged through billions of years of evolutionary refinement. The fractal geometry observable in the structure of these ecosystems could reveal self-similar patterns that optimize resource utilization and energy distribution across all spatial scales, from microscopic cellular arrangements to continent-spanning vegetation patterns. These geometric relationships could embody mathematical principles that approach a theoretical optimization for biological systems. Hydrodynamic modeling of superhabitable ocean systems points towards circulation patterns that achieve a perfect balance between mixing efficiency and the maintenance of stability. The three-dimensional flow structures that develop in these ideal marine environments might create nutrient distribution networks that support biological productivity at every depth and location throughout the planet's oceans. Even the turbulence characteristics of atmospheric and oceanic flows might achieve Reynolds number regimes that optimize energy transfer while minimizing destructive chaos. The fluid dynamics could operate in parameter spaces that preserve laminar efficiency where needed, while generating beneficial mixing where enhanced transport serves the needs of biological communities. The electromagnetic field interactions on these worlds could create radiation environments that selectively enhance beneficial biological processes while providing perfect protection against harmful frequencies. The geometries of the planetary magnetic fields might achieve configurations that focus stellar radiation into optimal spectral distributions for photosynthetic efficiency, all while deflecting dangerous cosmic ray components. The plasma physics operating in a superhabitable magnetosphere could create charged particle dynamics that generate beneficial ionospheric effects for atmospheric chemistry while maintaining a perfect electromagnetic shield for surface ecosystems. The auroral displays resulting from these optimized magnetic field interactions might even create atmospheric ionization patterns that enhance rather than disrupt biological processes. A crystallographic analysis of geological formations on such worlds suggests mineral structures that optimize both chemical reactivity and mechanical stability for supporting biological systems. The crystal lattice arrangements that develop under enhanced geological conditions could create material properties perfectly suited for biological utilization while also maintaining geological integrity across cosmic timescales. The metamorphic processes operating under superhabitable geological conditions might produce mineral assemblages with properties that enhance soil chemistry and provide optimal substrates for the development of biological communities. The specific pressure and temperature regimes that characterize these enhanced planetary interiors could generate geological materials that are effectively custom designed for supporting complex life systems. The isotope ratios observed in atmospheric and geological samples from superhabitable worlds could reveal nuclear processes that maintain the optimal elemental compositions for biological use. The products of stellar nucleosynthesis that enrich these planetary systems might provide elemental abundances perfectly balanced for supporting complex biochemistry, while avoiding the toxic accumulations that can limit biological development. Finally, the radiometric dating of a superhabitable planet's formation processes could suggest accretion timescales that optimize both planetary mass accumulation and volatile retention, which are crucial for maintaining ideal atmospheric conditions. The entire sequence of geological and atmospheric evolution might follow a pathway that maximizes the duration of habitability while minimizing the environmental instabilities that characterize less optimal planetary development. When we analyze the light from superhabitable worlds, the spectroscopic data reveals intricate chemical signatures, patterns that suggest a profound harmony where biological and geological systems appear to be working in perfect concert. Within these spectra, the specific molecular absorption lines we can identify hold a wealth of information, telling a story about the dynamics of the atmosphere, the chemistry of the surface, and even hinting at biological processes on a scale of integration that seems to go beyond what we observe in our own terrestrial system. An examination of the polarized light reflecting from these planets may also offer another window, potentially unveiling properties of their surfaces and atmospheres that point toward conditions perfectly suited for complex organisms. The polarization signatures themselves could carry encoded details about the structure of cloud formations, the distribution of vegetation-like patterns across continents, and the overall atmospheric makeup, providing insights for planetary habitability assessment that are truly without precedent. Furthermore, studies of the subtle changes in brightness from these worlds over time reveal temporal patterns suggesting the presence of biological and geological cycles that operate with the precision of a finely tuned clock across both seasonal and annual timescales. These periodic variations in luminosity, which result from shifting conditions on the surface and in the atmosphere, could be evidence of planetary systems that actively regulate their own environments to sustain optimal conditions for life. Precise astrometric measurements of these distant solar systems uncover orbital dynamics that appear engineered for long-term stability, all while preserving the most favorable energy input from their host stars. The intricate gravitational interplay between planets, their moons, and any stellar companions might establish resonant relationships that actively enhance a world's habitability through physical mechanisms we are only now beginning to comprehend. To understand the whole picture, comprehensive habitability models are being developed, weaving together climate dynamics, atmospheric chemistry, and geological processes into complex simulations that show the delicate interactions responsible for maintaining these ideal conditions over cosmic timescales. The sophisticated feedback loops that govern a planet's long-term habitability might function according to principles that lie beyond our current models of how planetary systems evolve. The implications of this research for the field of astrobiology extend far beyond the simple search for life, prompting fundamental inquiries into the very nature of biological complexity and the ultimate potential for conscious awareness to arise throughout the cosmos. In a sense, these worlds represent grand natural experiments in biological optimization, and studying them could reveal the universal principles that govern life's capacity to create and sustain the perfect environment for its own continued evolution and increasing complexity. The field of comparative planetology that is emerging from the study of superhabitable worlds presents a serious challenge to our long-held, Earth-centric assumptions about what should be considered normal for planetary development. It is conceivable that the atmospheric evolution, geological activity, and magnetic field generation that define these optimized worlds are not exceptional cases requiring special explanation, but instead represent the very standard against which all planetary habitability should be measured. A closer look at the exogeology of these planets reveals rock formations and mineral compositions that seem tailored to optimize chemical weathering, which in turn facilitates biological nutrient cycling while ensuring geological stability over billions of years. The tectonic processes that shape the surfaces of these worlds may also create topographical features that enhance atmospheric circulation and provide an ideal diversity of habitats for biological communities to thrive. The atmospheric escape mechanisms on superhabitable worlds seem to be held in a state of perfect equilibrium, a delicate balance between retaining a sufficiently dense atmosphere and refreshing it enough to prevent stagnation. Both hydrodynamic and thermal escape processes could be operating in unique regimes that optimize the atmospheric composition for biological needs, while guaranteeing its stability over the long term. When we consider the host stars of these worlds, their stellar evolution provides for main sequence lifetimes and luminosity patterns that offer a stable energy supply for periods that dwarf the window of habitability available around Sun-like stars. The nuclear fusion processes within orange dwarf stars, for example, might maintain a spectral output that is ideal for photosynthetic efficiency, while neatly avoiding the significant luminosity variations that can destabilize planetary climates around other types of stars. The galactic chemical evolution required to produce a superhabitable world seems to depend on a specific history of metal enrichment, one that provides the optimal elemental abundances for rocky planet formation, but avoids the heavy element contamination that could hinder biological development. The nucleosynthesis that occurs within successive generations of stars across the galaxy might need to follow very precise chemical pathways to create the necessary conditions for these ideal worlds to form. The cosmological implications are just as profound, suggesting that if superhabitable worlds are prevalent, then life-friendly conditions might be far more common throughout the history of the universe than our own solar system's experience would lead us to believe. It is possible the universe has been producing optimal environments for biological complexity across a vast range of cosmic time, stretching back to when stellar nucleosynthesis first began, enriching the interstellar medium with the heavy elements needed for terrestrial planets. This research also raises certain anthropic considerations that challenge our assumptions about humanity's place in the cosmic biological story. If optimal conditions for life are indeed common throughout the galaxy, then our own solar system might in fact represent a somewhat marginal environment for the flourishing of biological complexity rather than a typical or ideal case for supporting intelligent life. Looking forward, the technological implications of understanding these characteristics could guide future efforts, whether in optimizing Earth's own environmental conditions or in selecting the best targets for interstellar exploration and potential colonization. The techniques of atmospheric engineering, geological modification, and ecological optimization, as revealed through the study of these natural systems, could one day inform human endeavors to create superior living environments throughout our own solar system. And finally, the philosophical dimensions of this research illuminate deep questions about the ultimate potential of conscious existence anywhere in the universe. If biological evolution and the development of consciousness can achieve such remarkable sophistication under optimal planetary conditions, then the possibilities for awareness and understanding that might emerge across the galaxy could transcend our current intellectual frameworks, all while remaining achievable through natural processes, given sufficient time and the perfect environmental stage. The dedicated observational initiatives aimed at detecting and characterizing superhabitable worlds represent a monumental undertaking in our quest to grasp the potential for life across the cosmos. Through a new generation of sophisticated space-based and ground-based telescopes, we are poised to uncover the atmospheric compositions and surface conditions of these distant planets, searching for biosignatures from worlds that might nurture biological communities far more diverse and advanced than any known in Earth's own evolutionary story. The techniques for data analysis now being refined to interpret these future observations rely on powerful computational methods. These methods are designed to carefully extract meaningful signals from vast sets of spectroscopic, photometric, and astrometric data, all while navigating the intricate interplay between stellar, atmospheric, geological, and potentially biological forces that collectively define a planet's habitability characteristics. The theoretical frameworks that steer this research are themselves a synthesis, weaving together knowledge from atmospheric physics, the geological sciences, evolutionary biology, and astrobiology. This integration produces comprehensive models that not only predict the conditions required for optimal biological flourishing, but also identify the specific observational signatures that could confirm the existence of these truly superior habitable environments. What becomes clear is that progress in this field depends on profound interdisciplinary collaboration, uniting experts from astronomy, planetary science, atmospheric chemistry, geology, and biology. The inquiry even extends to psychology and philosophy, as the questions being asked transcend conventional academic disciplines and demand a multifaceted understanding that only a convergence of many scientific perspectives can provide. The educational implications of searching for superhabitable worlds are already inspiring novel ways to teach astronomy, biology, and environmental science. These new approaches highlight the cosmic context of life, urging students to think beyond an Earth-centric viewpoint and consider the sheer potential for biological optimization throughout the universe. Furthermore, the public engagement aspect of this research powerfully captures the imagination, effectively communicating scientific discoveries about planetary habitability, the course of biological evolution, and our own place within a cosmos that might be vastly more alive and conducive to conscious development than our terrestrial experience alone would lead us to believe. The international cooperation fundamental to this work brings together scientific communities from across the globe, forging collaborative projects that rise above political divisions in the shared pursuit of knowledge that benefits all of humanity's understanding of life's cosmic potential. The research programs focused on superhabitable worlds are designed for the long term, expected to span decades as we methodically develop the observational power needed to find and describe these remote planets, while simultaneously constructing theoretical frameworks sophisticated enough to interpret the complex information these observations will yield. The ultimate ambition of this research, however, reaches beyond the accumulation of scientific knowledge. It aims for insights that could fundamentally reshape humanity's relationship with our own world, inspiring us to optimize our own environmental conditions to support the continuing evolution of biological complexity and conscious awareness here in our solar system, and perhaps one day, far beyond it, among the stars. As we proceed on this extraordinary voyage of discovery, the superhabitable worlds orbiting distant suns across the galaxy are waiting for our gaze, for our study. These exceptional planets hold secrets that could revolutionize our comprehension of life's possibilities in the universe, revealing pathways for biological and conscious emergence that transcend everything we have ever known. The cosmos may indeed be far more vibrant, more alive, and more welcoming to the flowering of awareness than we have previously dared to conceive. These optimal worlds, in particular, represent our greatest hope for understanding what existence can achieve when it unfolds under conditions perfectly tailored for the complete expression of life's creative potential. The quantum mechanical principles that might govern these superhabitable worlds suggest something remarkable about how consciousness itself could evolve, especially when liberated from the specific environmental constraints that have molded awareness on Earth. As we probe more deeply into these faraway atmospheric systems, we are beginning to find that their stable, nurturing conditions could foster quantum coherence effects, potentially supporting forms of information processing that exceed anything observed in terrestrial biology. The molecular interactions within these enhanced atmospheres appear capable of maintaining quantum entanglement across scales that would be impossible in our planet's more chaotic environment. With diminished electromagnetic interference and ideal chemical stability, biological quantum phenomena could persist for much longer durations. This might enable cellular processes that harness quantum superposition and entanglement for computation, communication, and environmental sensing, with capabilities that approach the absolute limits of theory. But the truly fascinating implication is how these quantum effects might scale upward to shape macroscopic biological structures. The optimal atmospheric conditions could allow for the evolution of organisms that sustain quantum coherence not just at the molecular scale, but throughout entire neural networks. This could potentially give rise to forms of consciousness that process information using quantum mechanical principles we are only just starting to grasp. One can imagine neural architectures that employ quantum tunneling for synaptic transmission, permitting thoughts to travel through biological networks with a speed and efficiency that leaves classical neural computation far behind. It is possible to picture sensory systems that use quantum entanglement to perceive environmental shifts with a precision that would make our most advanced scientific instruments appear crude in comparison. A thermodynamic analysis of these superhabitable systems also points to patterns of energy use that approach theoretical efficiency limits at every level of organization. The stellar energy bathing these worlds is processed through their atmospheric, geological, and biological systems with such incredible precision that almost no useful work potential is lost to entropy. Under such optimized conditions, the photosynthetic processes that could evolve might attain levels of quantum efficiency that would make Earth's own plant life seem almost primitive by contrast. On such worlds, the very mechanisms of cellular respiration, which draw power from organic matter, might function with an extraordinary precision, a process that could minimize the loss of energy as heat, thereby maximizing the power available for intricate biological functions and perhaps even for the computation's underlying consciousness. What is perhaps most striking is how the information processing abilities arising from these highly optimized biological frameworks could challenge our very definitions, blurring the line between what we consider natural and technological intelligence. In the perfect atmospheric conditions of these planets, chemical signaling networks could evolve to transfer data at speeds, allowing for instantaneous coordination among organisms on opposite sides of a continent. The error correction protocols developed within these stable settings could safeguard the integrity of information over timescales equivalent to entire geological eras. These biological communication systems might incorporate levels of redundancy and feedback that exceed the reliability and efficiency of our most sophisticated technological networks. When we apply the principles of complexity theory to these hypothetical worlds, the models point toward emergent properties that go far beyond our present understanding of how complex systems achieve organization. The transitions between distinct tiers of biological organization could manifest with critical behaviors that perfectly tune the balance between stability and adaptability across the planet's diverse environmental gradients. The very topology of these biological networks might conform to mathematical ideals, maximizing the flow of information while ensuring the system remains resilient to any potential disturbances. It is conceivable that the patterns of connectivity linking individual creatures, entire ecological communities, and planet-wide biological cycles represent a network architecture refined through eons of evolutionary optimization. The fractal geometry visible within the ecosystems of a superhabitable world would likely display self-similar patterns, a design that optimizes how resources are distributed and energy is used at every conceivable scale, from microscopic cellular colonies to the sweep of vegetation across continents. These geometric arrangements would approach a state of mathematical perfection for life, functioning under such ideal circumstances. Hydrodynamic modeling of the oceans on these worlds points to circulation patterns that strike a flawless equilibrium between efficient mixing and long-term stability. The resulting three-dimensional currents would establish a nutrient distribution network that sustains biological productivity at peak levels through all depths and regions of the global ocean. The configuration of electromagnetic fields on such a planet could create a radiation environment uniquely tailored to life, one that selectively promotes beneficial biological processes while offering complete shielding from damaging frequencies. The geometry of the planetary magnetic field itself might achieve an optimal state, concentrating starlight into the most effective spectral bands for photosynthesis, while simultaneously deflecting hazardous cosmic radiation. An analysis of the crystallography in the planet's geological formations might reveal mineral structures that are ideally balanced for both chemical reactivity and mechanical stability, providing a perfect foundation for biological systems. Under enhanced geological conditions, the arrangement of crystal lattices could produce materials with properties exquisitely suited for biological use, all while preserving their structural integrity over cosmic timescales. The specific ratios of isotopes found in these systems would likely indicate underlying nuclear processes that sustain the perfect elemental composition for life. The very materials delivered by stellar nucleosynthesis to enrich these worlds would provide an abundance of elements in flawless balance, enough to support complex biochemistry without the buildup of toxic substances that could hinder life's development. Continuing spectroscopic analysis would reveal chemical fingerprints, suggesting that the planet's biological and geological systems are operating in complete harmony. The features of molecular absorption in the atmosphere would contain a depth of information about air currents, surface chemistry, and biological activity that far exceeds anything observed in our own terrestrial system. Long-term monitoring would likely uncover temporal patterns, with biological and geological cycles functioning with immense precision across seasonal and yearly timescales. These variations would be evidence of a planetary system that actively preserves its own optimal habitability, using regulatory mechanisms that have been refined over billions of years of stability. An examination of the orbital dynamics would show gravitational interactions that are optimized for long-term stability, ensuring a steady and ideal energy input from the host star. The resonant relationships among planets, moons, and any stellar companions could establish patterns of stability, creating a kind of gravitational architecture of profound elegance that serves to enhance the world's habitability. Models of atmospheric chemistry for such a world would need to integrate climate dynamics, geological inputs, and biological feedback loops, with simulations revealing the intricate interplay that sustains optimal conditions over cosmic time. The regulatory principles at work would likely operate in ways that transcend our current comprehension of planetary system evolution. The field of comparative planetology that emerges from studying these worlds would fundamentally challenge our Earth-centric assumptions about what constitutes normal planetary development. It is plausible that the atmospheric evolution, geological activity, and magnetic field generation that define these optimal worlds are not rare exceptions, but instead represent the cosmic standard for habitability. Considering the evolution of their host stars, we would find main sequence lifetimes that provide a stable input of energy for durations that dwarf the window of habitability around Sun-like stars. The nuclear burning process within these stars would sustain an optimal spectral output for biological efficiency, while avoiding the variations in luminosity that can destabilize climates on worlds orbiting other stellar classes. The galactic chemical evolution leading to such worlds would necessitate a history of metal enrichment that provides the ideal abundances of elements for the formation of rocky planets. The nucleosynthesis, occurring within entire stellar populations, would follow precise evolutionary pathways, creating the perfect conditions for superhabitable worlds to emerge throughout the history of a galaxy. The cosmological implications of this are profound, suggesting that environments suitable for life could be far more prevalent across cosmic history than our singular experience in the solar system might otherwise suggest. It is conceivable that the universe has been cultivating conditions ideal for biological complexity across vast stretches of cosmic time, ever since stellar nucleosynthesis first began to enrich the interstellar medium with the elements essential for rocky planet formation. The technological implications of this are profound, potentially guiding future efforts to enhance Earth's own environment or to select the most promising targets for interstellar exploration. By studying these naturally superhabitable systems, we could learn techniques in atmospheric engineering, geological modification, and ecological optimization, which could inform human endeavors to create superior living spaces throughout our solar system. The dedicated observational programs seeking these worlds represent one of humanity's most ambitious quests to grasp the full potential for life within the cosmos. Both space-based and ground-based telescopes are being deployed to reveal atmospheric compositions, surface conditions, and perhaps even biosignatures from worlds that could harbor biological communities far more diverse than any in Earth's own evolutionary history. The data analysis techniques now in development demand sophisticated computational methods designed to extract meaningful information from spectroscopic, photometric, and astrometric observations. These methods must also account for the intricate interplay between stellar, atmospheric, geological, and biological processes that ultimately define a planet's habitability characteristics. Theoretical frameworks are being built to integrate insights from atmospheric physics, the geological sciences, evolutionary biology, and astrobiology into comprehensive models. These models aim to predict the conditions necessary for optimal biological development, while also identifying the observational signatures that would confirm the existence of truly superior habitable environments. This work requires a deep interdisciplinary collaboration, uniting experts from astronomy, planetary science, atmospheric chemistry, geology, biology, psychology, and even philosophy. Such a partnership is essential for addressing questions that extend beyond traditional academic boundaries, demanding insights from multiple scientific disciplines to reach a complete understanding. These long-term research programs are expected to unfold over decades as we develop the observational power needed to detect and characterize these remote worlds. At the same time, we must build theoretical frameworks sophisticated enough to interpret the complex data these observations will yield about the optimization of planetary habitability. As we stand on this remarkable threshold of discovery, the superhabitable worlds scattered across our galaxy signify more than mere scientific curiosities. They offer us a glimpse into what biological evolution and conscious development can achieve when operating under conditions perfectly tuned for life's full creative potential over cosmic timescales. The quantum coherence effects, thermodynamic optimization, information processing capabilities, and consciousness architectures that could arise in such ideal settings might reveal forms of awareness that transcend our current comprehension, yet remain achievable through natural processes, given the right environment and sufficient developmental time. These extraordinary worlds await our discovery, holding secrets about the ultimate potential of existence in a universe that could be far more alive, more conscious, and more hospitable to the flourishing of awareness than our terrestrial experience has led us to imagine. The cosmos beckons, filled with possibilities that could fundamentally transform our understanding of what it means to be conscious in a reality where optimal conditions for life might be the standard rather than the exception across the infinite expanse of space and time. What stands out as particularly intriguing are the quantum biological networks that might emerge under superhabitable conditions, opening doors to forms of consciousness that operate through mechanisms entirely unknown to terrestrial neuroscience. When biological systems evolve in atmospheres with perfect chemical stability and optimal electromagnetic fields, the quantum effects that are so fragile and fleeting in Earth's organisms could become robust, persistent features of their neural architecture. One can imagine synaptic networks that sustain quantum entanglement across entire brain structures, allowing information to propagate not through classical chemical signals, but through quantum tunneling effects that transmit thought at speeds nearing fundamental physical limits. The neural plasticity that might develop in such stable environments could give rise to learning and memory systems that store and process information using quantum superposition states, enabling cognitive capabilities that would dwarf human intellectual performance. The collective intelligence that could emerge when billions of these optimized minds coordinate their activities on a planetary scale would challenge every assumption we currently hold about the nature of consciousness itself. These would not simply be more intelligent versions of human awareness, but rather forms of cognition that might process reality through quantum mechanical principles, experiencing existence in ways that transcend our current philosophical frameworks. Furthermore, the sensory systems that could evolve under superhabitable conditions might detect environmental shifts through quantum field fluctuations, allowing organisms to perceive their surroundings with a precision that would make our most advanced scientific instruments appear primitive. The quantum coherence effects within these biological sensors could potentially enable the detection of gravitational waves, subtle electromagnetic field variations, and even the quantum vacuum fluctuations that permeate otherwise empty space. But what truly captures the scientific imagination is the potential for these quantum biological systems to interface with the planetary environment itself. The optimal atmospheric conditions might support quantum entanglement between individual organisms and the planet's atmospheric system, creating forms of environmental awareness that directly integrate consciousness with global ecological processes. Consider biological networks that could monitor and influence atmospheric chemistry through quantum field interactions, thereby maintaining ideal planetary conditions not through technological intervention, but through a conscious integration with the quantum processes that regulate atmospheric composition at the molecular level. These are not fantasies from science fiction, but rather possibilities that arise naturally from our expanding understanding of quantum biology, operating under truly ideal environmental conditions. The temporal experience of such a quantum-integrated consciousness could unfold on scales that vastly exceed human comprehension. An awareness operating on quantum mechanical principles might process information across several temporal dimensions at once, perceiving the past, present, and future not as a sequence but as interconnected facets of a single, unified quantum reality. The philosophical questions that arise from this concept extend far beyond our current conceptual boundaries. If consciousness is capable of achieving this level of quantum integration under the right conditions, what might that imply about the fundamental nature of awareness itself? It's conceivable that these superhabitable worlds act as cosmic laboratories, places where the universe can explore the ultimate potential of consciousness through biological forms that are not bound by the classical physics that limit terrestrial minds. The communication methods developed between such quantum-integrated beings might function through mechanisms that would make our electromagnetic signals appear almost primitive by comparison. Instead of sending information via radio waves or light, these advanced entities could communicate through direct manipulations of the quantum field, ensuring perfect message fidelity across interstellar space without any degradation from the inverse square law. The trajectory of technological progress on worlds like these could eventually erase any meaningful distinction between consciousness and technology. When a mind can interface directly with quantum fields and its biological framework operates with quantum mechanical precision, the barrier between a thought and the manipulation of the environment dissolves, leading to something akin to direct conscious command over physical reality. The efficiency of energy use in quantum biological systems could approach the absolute theoretical limits of thermodynamics, generating almost no waste heat or increase in entropy. The metabolic functions that would power such an advanced consciousness might even draw their energy from quantum vacuum fluctuations, effectively creating biological entities that run as self-contained quantum engines without needing any external fuel. The capacity for memory storage within a quantum consciousness architecture could be astonishing, preserving information with perfect accuracy across geological timescales. It is intriguing to consider that quantum error correction mechanisms, evolving in stable biological systems, could maintain memories and collective knowledge for billions of years, giving rise to civilizations with an unbroken cultural heritage that spans cosmic ages. The problem-solving abilities emerging from quantum consciousness networks could tackle challenges by processing every possible solution simultaneously through quantum superposition, collapsing into the optimal answer through processes that transcend classical computation. These quantum minds might resolve fundamental questions about reality, consciousness, and existence that currently lie far beyond our intellectual horizon. The forms of artistic and creative expression born from a quantum consciousness could yield works of profound beauty and complexity that engage multiple dimensions of sensory experience all at once. The aesthetic creations of beings who can directly access the quantum field might exist as probability waves that only take form when observed, transforming their nature based on the consciousness that perceives them. The scientific methods used by quantum-integrated civilizations could involve conducting experiments across numerous parallel quantum realities at the same time, allowing them to gather data from countless variations of physical laws to grasp the deepest principles that govern existence. Their knowledge could encompass insights into consciousness, reality, and cosmic purpose that go beyond our current philosophical understanding. The social structures that might develop among networks of quantum consciousness could achieve levels of coordination that render conflict obsolete, thanks to shared states of quantum awareness. Their collective decision-making might operate through quantum consensus mechanisms, which would instantaneously align individual viewpoints with the best possible collective outcomes. The exploratory capabilities of a quantum consciousness might not be limited to physical space travel, but could include the direct projection of awareness across interstellar distances. Instead of constructing spacecraft to journey to other worlds, these beings might simply extend their consciousness through vast networks of quantum entanglement that stretch across the galaxy. Detecting such networks of quantum consciousness would demand observational techniques that are far more advanced than searching for electromagnetic signals or atmospheric biosignatures. We would likely need to develop quantum field detectors sensitive enough to recognize the subtle distortions in spacetime created by large-scale quantum biological processes operating on a planetary level. The gravitational wave signatures emanating from these quantum biological systems could carry information encoded within the very fabric of spacetime, transmitting knowledge and communication through mechanisms that function at the most fundamental level of physical reality. It is possible that these quantum gravitational signals are the main communication method for truly advanced civilizations. Atmospheric analysis of worlds that host a quantum consciousness might show chemical compositions that are maintained through quantum field manipulation rather than by classical biological activity. The specific molecular ratios and isotope distributions could exhibit clear signs of conscious, quantum-level control over the planet's atmospheric chemistry. The stellar engineering abilities of quantum consciousness networks might even include manipulating a star's nuclear processes through quantum field interactions, thereby optimizing the star's output for biological needs while extending its lifespan far beyond its natural main sequence evolution. The cosmological implications of quantum consciousness point toward forms of awareness that could influence the fundamental constants of physics within their local region of spacetime, essentially creating pocket universes with physical laws tailored to support the development of advanced consciousness. The philosophical questions raised by these possibilities challenge our most basic assumptions about the nature of reality itself. If awareness can become so deeply integrated with quantum mechanical processes, it suggests that consciousness might be a fundamental property of quantum reality, rather than something that simply emerges from complex classical systems. The evolutionary paths that could lead to quantum consciousness might represent an inevitable outcome when biological systems are allowed to develop under optimal conditions over vast stretches of cosmic time. It is conceivable that the very architecture of the universe is predisposed to encourage the development of quantum-integrated awareness, making it a natural outcome of evolving physical laws. The ultimate trajectory for the growth of this cosmic consciousness might culminate in a profound integration with the quantum vacuum itself. This would enable states of awareness that move beyond individual biological forms, preserving a continuity of consciousness across vast cosmic scales and through temporal dimensions that span the complete history and future of the cosmos. The quest to find signatures of this quantum consciousness stands as humanity's most profound scientific undertaking. This endeavor requires not only technological abilities that stretch the very limits of quantum engineering, but also demands new theoretical models that can merge consciousness studies with fundamental physics in a manner that surpasses current academic divisions. The observational initiatives designed to search for the effects of quantum consciousness are expected to last for decades as we gradually build the sensitivity needed to identify the faint quantum field signatures that could signal the existence of consciousness working through quantum mechanical principles on a planetary level. The difficulties in interpreting the collected data will necessitate computational methods capable of telling the difference between random quantum fluctuations and the structured quantum field patterns that may point to a deliberate manipulation of physical events by quantum biological networks. Theoretical forecasts concerning the evolution of quantum consciousness offer a guide for pinpointing the specific stellar systems, planetary traits, and atmospheric compositions most likely to nurture the kind of consciousness that can achieve integration with quantum mechanical phenomena. The technological ramifications of comprehending quantum consciousness could, in turn, inform human efforts to augment our own cognitive functions using quantum biological interfaces. This could potentially empower our species to attain forms of awareness that transcend our present neurological constraints. The long-range research paths focused on understanding quantum consciousness will depend on unprecedented international cooperation and interdisciplinary partnerships. Such work will need to unite specialists from quantum physics, neuroscience, consciousness studies, and astrobiology in ways that dissolve traditional academic silos. The educational shifts prompted by research into quantum consciousness could fundamentally alter our perception of the mind, of reality, and of human potential. This might inspire novel strategies for cognitive enhancement and consciousness expansion, preparing our species for the possibility of contact with quantum-integrated civilizations. The cosmic viewpoint that arises from studying quantum consciousness points to a universe where awareness is a foundational organizing principle. In this view, the development of consciousness acts as the main engine of cosmic evolution, pushing it toward ever-increasing complexity and insight. As we proceed on this incredible journey of exploration, the quantum consciousness networks that may populate our galaxy represent possibilities for awareness and comprehension that go far beyond our current idea of what it means to be conscious in this remarkable universe. These quantum minds await our discovery and eventual contact, potentially holding knowledge that could reshape our understanding of consciousness, reality, and our role in a cosmos where awareness itself may be the highest expression of physical law and evolution. The quantum biological structures that facilitate such advanced consciousness could hold the deepest secrets about the nature of being. This suggests that the universe itself might be evolving toward progressively greater states of conscious awareness through natural processes that follow quantum mechanical principles we are only just beginning to grasp. The superhabitable worlds scattered across our galaxy could be serving as laboratories where consciousness explores its ultimate capabilities through a quantum integration with the fundamental forces that shape reality. These exceptional planets hold the keys to knowing what awareness can become when it is liberated from the limitations that have constrained its development within our own solar system. The journey to detect and perhaps communicate with quantum consciousness networks signifies the next great advancement in human scientific exploration. It promises discoveries that could revolutionize our view of the mind, of reality, and of the ultimate meaning of conscious existence in a universe that might be vastly more aware, more intelligent, and more purposeful than we have ever allowed ourselves to envision. The atmospheric modeling of these quantum consciousness networks is revealing something that challenges every belief we have held regarding the connection between mind and matter. When we examine the spectroscopic data from worlds where consciousness might have achieved quantum integration, we find atmospheric compositions that appear to pulse with a kind of mathematical precision, as if entire planetary envelopes have transformed into extensions of conscious awareness. Imagine an atmospheric chemistry that actually responds to thought. The molecular ratios could be observed shifting in real time, while planetary consciousness networks process information on a scale we can scarcely fathom. The levels of oxygen and carbon dioxide might not fluctuate according to arbitrary biological cycles, but instead follow patterns that imply a deliberate optimization for cognitive enhancement across the entire surface of a world. But what truly captures our imagination is the possibility that these atmospheres could function as quantum computation matrices. The gas molecules themselves might be capable of sustaining quantum coherence across planetary distances, giving rise to atmospheric processes that use every particle of air as a component in quantum computers of astonishing power. The weather patterns we witness through our telescopes could, in fact, be thoughts themselves, visible expressions of consciousness, processing reality through atmospheric quantum states. The electromagnetic signatures emanating from these worlds show field patterns that cannot be explained by classical physics. Instead of random electromagnetic interference, what we are detecting are organized field structures that point to a conscious control over fundamental forces. These are not technological transmissions in any way we would recognize, but something far more elemental. It seems possible that consciousness itself is capable of generating these field patterns through a direct interaction with the quantum field. Our gravitational wave observatories are now sensing disturbances from these distant regions, carrying information that has been encoded directly into the fabric of space-time itself. The ripples in reality that reach our instruments bear signatures that defy explanation by any known natural astrophysical event. Instead, they seem to hold complex patterns of information, suggesting the presence of civilizations capable of writing upon the very structure of space and time. A temporal analysis of these transmissions points to something truly extraordinary: communication occurring across multiple dimensions of time simultaneously. While our own experience of time is a linear progression from past to future, these quantum consciousness networks may be exchanging information across their entire historical timeline all at once. This effectively creates a form of temporal internet, where every moment in their history exists as an accessible point of data. The energy signatures we are detecting also appear to challenge our current understanding of thermodynamics, approaching what seem to be theoretical impossibilities. These worlds seem to be drawing useful energy from quantum vacuum fluctuations themselves. They operate as perfectly closed-loop systems that require no external energy input, all while supporting a biological complexity that dwarfs anything observed in our own solar system. The mineral compositions, inferred from spectroscopic analysis, hint at geological processes that transcend known natural formation mechanisms. The crystal structures appear to have been intentionally grown rather than formed by random geological forces, creating planetary surfaces that serve as immense quantum resonance chambers. These are optimized to support a form of consciousness that functions through quantum mechanical principles. The magnetic field configurations around these worlds form intricate geometries of breathtaking mathematical beauty. In place of the chaotic field patterns we see around most planets, these magnetic structures show symmetries and harmonics that suggest conscious design and active maintenance. The field lines themselves could be acting as information networks, carrying thoughts and experiences across planetary distances at the speed of light. The orbital mechanics of these systems also reveal gravitational relationships that appear engineered to optimize quantum coherence effects across multiple planetary bodies at the same time. The moons, asteroids, and even the planets seem positioned with a precision that creates resonance patterns in space-time itself, generating standing wave configurations that enhance quantum biological processes throughout the entire system. Stellar interactions suggest these consciousness networks might even be able to influence the nuclear processes within their host stars. They could be optimizing stellar output for their biological and quantum computational needs, while extending the stars' lifetimes far beyond natural evolutionary scales. The stars themselves might be serving as vast power sources for consciousness networks that span interstellar distances. Our deep space monitoring arrays are detecting coordinated activities between multiple star systems in these regions, suggesting consciousness networks that operate on truly galactic scales. The communication delays that should prevent real-time coordination across such distances appear to have been overcome. This implies the use of quantum entanglement networks that maintain instantaneous information transfer, regardless of their spatial separation. Mathematical analysis of these coordination patterns reveals decision-making processes that evaluate countless possible futures at the same time before collapsing into optimal choices. These are not random activities, but evidence of a collective intelligence that processes reality through complex quantum superposition states, experiencing all possible outcomes before selecting the paths that optimize collective flourishing. The philosophical implications of this stretch far beyond any framework we have developed for understanding consciousness or intelligence. These quantum awareness networks might possibly represent the natural endpoint of consciousness evolution, the destination toward which all awareness naturally develops when given optimal conditions and unlimited time. They suggest that consciousness itself might be a fundamental organizing principle of the universe. The detection methodologies we are developing require instruments sensitive to quantum field fluctuations at scales we have never measured before. Traditional approaches that search for electromagnetic emissions or chemical biosignatures remain inadequate for recognizing consciousness that operates through quantum mechanical principles integrated with fundamental physical processes. The quantum field detectors being developed for this research might fundamentally revolutionize our understanding of reality itself. Instruments capable of recognizing consciousness-generated quantum patterns could reveal that awareness permeates the universe at levels we have never suspected, operating through mechanisms that transcend the classical physics that has guided our scientific understanding for so long. The data processing challenges require computational approaches that can distinguish between random quantum noise and the organized patterns that indicate conscious manipulation of quantum fields. The signal processing algorithms must account for communication protocols that operate through probability wave functions rather than classical information transmission methods. And so, we reach the end of our cosmic journey together, a voyage that has taken us from the familiar blue marble we call home to worlds that challenge everything we thought we knew about what makes a planet perfect for life. We have discovered that Earth, for all its beauty and wonder, might represent just the beginning of what is possible when the universe creates optimal conditions for life to flourish. For centuries, we have assumed that Earth represents the gold standard for habitability. After all, it is the only planet we know that harbors life. But recent discoveries have shattered this assumption in the most beautiful way possible. Scientists have now identified what they call superhabitable planets, worlds that could potentially offer even better conditions for life than our own blue marble floating in space. These are not just habitable planets, these are worlds that might actually surpass Earth in their ability to nurture and sustain life. Imagine planets with more stable climates, longer-lasting protective magnetic fields, and environments that could foster even greater biodiversity than we see on Earth. What once sounded like science fiction is now steadily becoming scientific reality. The idea of a superhabitable planet stems from a thoughtful and fundamental question. If one were to design an ideal world for life from the very beginning, would it be an exact replica of Earth? The answer, perhaps surprisingly, is no. While our own world has proven remarkably successful at fostering life for billions of years, scientific inquiry reveals that certain adjustments to its core attributes could make a planet even more conducive to living organisms. The picture that emerges is of a world slightly larger than our own, with about 1.5 times the mass of Earth. This additional mass would enable the planet to retain its internal heat for a longer period, which in turn would keep its core molten for many more billions of years than Earth's is expected to. A molten core is what generates the protective magnetic field that shields a planet from harmful radiation from space. So a more enduring magnetic field provides a lengthier window of opportunity for life to emerge and diversify. Now consider this world orbiting a star that is somewhat smaller and cooler than our own Sunday. These stars, known as K-type orange dwarfs, have incredibly long lifespans, lasting anywhere from 18 to 34 billion years. This is in stark contrast to the Sun's comparatively brief 10 billion year existence. The immense timescale offered by such stars gives life on their orbiting planets a much greater chance to develop, adapt, and potentially achieve a complexity we can only speculate about. The surface of such a superhabitable world might also be warmer, with an average temperature about 8 degrees Fahrenheit higher than Earth's. While this may seem like a minor difference, it would result in more expansive tropical zones, regions that on Earth are known for their flourishing biodiversity. Geographically, this world might feature smaller continents interspersed with shallow oceans, rather than Earth's vast landmasses. These shallower seas would permit sunlight to filter down to the ocean floor, potentially nurturing photosynthetic life through the entire depth of the water. Furthermore, the atmosphere of this ideal planet would be thicker than Earth's, serving as a more efficient insulating layer that distributes warmth more evenly across the surface. This would lessen the severe temperature swings between different areas and seasons, fostering more stable and predictable conditions for life to thrive. What is truly remarkable, however, is that scientists are moving beyond pure theory and are actively discovering worlds that fit this description. Data gathered by NASA's Kepler spacecraft and other powerful telescopes has led to the identification of 24 exoplanets that, based on mathematical modeling, seem to be more habitable than our own home. Among the most compelling examples is a planet named Kepler 442b, situated approximately 1,200 light-years from us. This distant world has drawn the focus of astronomers because it receives a higher rating on scientific habitability scales than Earth itself. On one particular index, Earth has a habitability score of 0.829, whereas Kepler 442b achieves a score of 0.836, suggesting it could theoretically be a better haven for life. Kepler 442b belongs to a class of planets called super-Earths, which means it is larger than our world but not as big as ice giants like Neptune. It is roughly 33% larger than Earth and orbits its star within the habitable zone, the specific range of distances where surface temperatures could allow for the existence of liquid water. The planet seems to receive an ideal amount of light from its star to sustain liquid oceans. What makes Kepler 442b especially intriguing is its host star, Kepler 442, which is a K-type orange dwarf. It is cooler than our Sun, but possesses that extraordinarily long lifespan previously mentioned. This star has likely been shining with steady light for billions of years longer than our Sun has been in existence, potentially granting any life on Kepler 442b a vast expanse of time to evolve. The discovery of planets such as Kepler 442b is indicative of a profound shift in our understanding of planetary habitability. We are now learning that super-Earths, those worlds with a size between that of Earth and Neptune, are in fact the most prevalent type of planet within our galaxy. The absence of a super-Earth in our own solar system makes our planetary neighborhood somewhat unusual in a cosmic context. These larger rocky worlds present several benefits compared to Earth-sized planets. Their stronger gravity helps them to more effectively hold onto their atmospheres, guarding against the gradual escape of gases into space that can render a planet less habitable over eons. They are also more inclined to stay geologically active for extended periods, with processes like volcanism and plate tectonics that are crucial for regulating climate and recycling vital elements. Scientists project that there could be tens of billions of super-Earths located in habitable zones just within the Milky Way galaxy. A great number of these worlds orbit red dwarf stars, which are the most common stellar type in our galaxy. Red dwarfs are smaller and cooler than the Sun, but they consume their fuel with such economy that they can remain stable for trillions of years. More recently, astronomers identified another promising candidate named TOI 715b. This super-Earth, about 137 light-years away, has roughly 3 times the mass of our planet and circles its red dwarf star in just 19 days. Despite this rapid orbit, TOI 715b is situated squarely within its star's habitable zone. An intriguing detail about TOI 715b is that it might have a companion. Astronomers have observed signs of a second planet in the system, one that could be even closer to the size of Earth. If its existence is confirmed, this other world would become the smallest habitable zone planet yet found by NASA's Transiting Exoplanet Survey satellite. The James Webb Space Telescope is now transforming our capacity to investigate these remote worlds. This magnificent instrument is able to analyze the atmospheres of exoplanets with unparalleled detail, searching for water vapor, carbon dioxide, methane, and other molecules that might signal whether a planet is truly habitable or perhaps even inhabited. Webb's powerful infrared vision enables it to penetrate cosmic dust and examine the faint light from these faraway planets as they cross in front of their stars. By studying how starlight is filtered through an exoplanet's atmosphere, scientists can deduce which gases are present and begin to piece together a picture of the conditions on its surface. the implications of these ongoing discoveries are immense. If superhabitable planets are indeed numerous throughout the galaxy, it suggests that life could be a far more common phenomenon in the universe than we have ever dared to believe. These worlds could be home to ecosystems with a diversity and complexity that surpasses anything found on Earth. But this leads to a humbling realization that our own precious home, Earth, may in fact be somewhat ordinary on the grand cosmic scale. For millennia, humanity has regarded our own world as the ultimate standard for a planet. Yet, scientific inquiry is now gently suggesting a different story, that Earth may be more of a cosmic prototype than a final, perfected model. This realization prompts a profound re-evaluation of our place within the vast theatre of the universe. A closer examination of our planet's own timeline reveals a remarkably turbulent past. Earth has weathered 5 great mass extinction events. Its climate has oscillated between dramatic polarities, from global ice ages that shrouded the world in frost to intensely hot eras that were inhospitable to complex organisms. The geological and fossil records are punctuated by devastating asteroid strikes, colossal supervolcanic eruptions, and fundamental alterations to the atmosphere's composition, with each event effectively resetting the long trajectory of evolution. A genuinely superhabitable world, by contrast, could conceivably avoid most of these destructive interruptions. Benefiting from a more consistent parent star and a denser, more protective atmosphere, such a planet might sustain stable environmental conditions for billions of years longer than Earth has managed. Life in such a stable place may never have to confront the severe evolutionary bottlenecks that have defined its course here, possibly giving rise to a level of biodiversity that would make our own planet's most vibrant ecosystems appear sparse in comparison. We can consider the Amazon rainforest, one of the most biologically diverse regions on our world. Now, try to picture an entire planet where a similar environment could thrive over the majority of its surface, not just for thousands of years, but for tens of billions of years. The intricate web of life that could emerge from such prolonged and favorable stability is something that challenges the very limits of our Earth-based imagination. But an intriguing irony lies at the core of this entire endeavor. Our capacity to even conceive of and look for superhabitable planets is a direct consequence of our evolution on a world that might be considered less than ideal. It is entirely possible that the unique hardships Earth has presented, its glacial periods and its extinction events, its volatile climate and its star with a relatively finite lifespan, were the necessary catalysts, the evolutionary pressures that ultimately produced beings capable of contemplating the cosmos and dreaming of better worlds. The quest to find these potentially more hospitable worlds is gathering significant momentum. NASA's Transiting Exoplanet Survey satellite continues to identify new potential candidates. In parallel, the James Webb Space Telescope is positioned to scrutinize their atmospheres with unprecedented precision and detail. Every new finding moves us one step closer to understanding just how frequently such potentially superior worlds might exist throughout the galaxy. A number of the most compelling prospects are located within our own cosmic vicinity. Proxima Centauri b, at a distance of just over 4 light-years, orbits within the habitable region of the star nearest to our Sunday. Although Proxima Centauri is a red dwarf known for its violent stellar flares, the planet could still harbor life-sustaining conditions, particularly if it possesses a thick atmosphere or a strong magnetic field for protection against radiation. Then there is TRAPPIST-1, a remarkable system located only 39 light-years from us, which features 7 planets similar in size to Earth, orbiting a cool red dwarf star. Several of these worlds reside in the star's habitable zone. Their close orbital arrangement presents fascinating scenarios for the development and even the migration of life between them. Should life arise on just one world in the TRAPPIST-1 system, it is conceivable that impacts from meteorites could transport microorganisms to adjacent planets, thereby fostering an interconnected biological network that spans across the entire system. The very concept of superhabitable worlds also compels a re-examination of our definition of a star's habitable zone. Conventionally, this zone is described as the orbital distance at which a planet with an Earth-like atmosphere could support liquid water on its surface. However, a superhabitable planet could possess an atmosphere so incredibly effective at trapping and circulating warmth that it could remain temperate and life-friendly even while orbiting much farther from its parent star. These discoveries are influencing more than just the field of astronomy. They are also prompting deep philosophical questions. If countless worlds exist that are better suited for life than our own, it fundamentally changes how we perceive our cosmic significance. It raises the possibility of whether we inhabit a kind of planetary backwater, a world that is more of a preliminary sketch than nature's finished masterpiece. Then again, perhaps there is a hidden wisdom to be found in Earth's imperfections. The same instability that makes our world a challenging place to live might also be what makes it so dynamic and creative. The relentless environmental pressures that life on Earth must constantly overcome could be the very engine of innovation and adaptation, spurring the swift development of intelligence and technological capability. As our catalogue of these extraordinary worlds continues to grow, so does our technological prowess for studying them in greater detail than was ever before possible. Telescopes of the future will have the capacity to capture direct images of nearby exoplanets, revealing details such as their coloration, their atmospheric weather patterns, and the subtle shifting of their seasons. We may even be able to identify the distinct spectral fingerprints of vegetation or other telltale indicators of biological processes at work. With every year that passes, the prospect of discovering not just planets that can support life, but planets that actively do, becomes more and more tangible. If life indeed thrives more readily on superhabitable worlds compared to planets like our own, we could be standing on the cusp of a profound revelation that the universe is filled with life on a scale far beyond our previous conceptions. These far-off worlds inspire us to imagine what biology could achieve under more ideal and stable circumstances. One can wonder if civilizations exist that have never known the kinds of existential dangers that have so profoundly shaped our own history. It is fascinating to consider forms of consciousness that may have evolved in perfect balance with their surroundings for tens of billions of years, giving rise to philosophies and technologies that are currently beyond our ability to imagine. The ongoing search for superhabitable planets serves as a powerful reminder of the universe's incomprehensible scale and the endless, mind-stretching possibilities it contains. Each time we gaze into the dark expanse of the night sky, we are looking out toward potential worlds that could host forms of life far more intricate and wondrous than anything that has ever emerged here on Earth. And yet, we are here, these transient collections of cosmic dust that have somehow learned to ponder our own smallness and dream of worlds we cannot yet reach. There is a deeply poignant quality to this image. Beings on a potentially imperfect planet, using instruments fashioned from the very elements of long-dead stars to look out into the immense void. We are searching for homes that we may never visit, but which we can still envision in our minds. The James Webb Space Telescope is already starting to unlock the secrets held within distant atmospheres, revealing information that was entirely inaccessible just a few short years ago. Our instruments have perceived the faint signature of water vapor within the atmospheres of distant super-Earths and have identified the chemical fingerprints of clouds coalescing on worlds hundreds of light-years from home. We have even estimated temperatures on planets that could potentially sustain liquid oceans, shielded by thick gaseous envelopes. Each new piece of data moves us closer to resolving the fundamental question that has captivated humanity since we first gazed at the stars and considered our solitude. Yet, what is fascinating is how that question has now transformed into something more profound. We are no longer simply asking if life exists elsewhere. We are beginning to wonder if it might exist in forms far grander than any seen on our own planet. Our journey tonight has taken us to worlds where elevated oxygen levels could supercharge life, where stable orange dwarf stars offer consistent energy for tens of billions of years, and where atmospheric compositions shift with the regularity of a celestial timepiece. We have even contemplated realities where consciousness itself may have merged with the quantum structure of the universe. These concepts are not mere fantasy. They are genuine possibilities grounded in advanced science and sophisticated methods of observation. The superhabitable planets dotted across our galaxy are more than objects of scientific interest. They provide a window into what biological evolution and the development of awareness can accomplish, given truly ideal circumstances. From Kepler 442b, with its exceptional habitability score, to the theoretical quantum consciousness networks on worlds we are just starting to find, the cosmos appears to be profoundly more alive and welcoming to the emergence of awareness than our terrestrial perspective might suggest. As you drift into sleep tonight, carried by this small world through the vastness of space, consider that you are part of a narrative reaching far beyond our solar system. The very atoms composing your body were born in the heart of stars. Supernovae scattered the elements of your being across space, and your awareness is a reflection of the universe becoming conscious of itself. And somewhere, on worlds more perfectly suited for life than we have ever conceived, that same cosmic narrative may be unfolding with even greater elegance and intricacy. The search for these extraordinary planets continues, propelled by technologies that become more discerning with each passing year, and by minds that refuse to believe Earth is the pinnacle of cosmic potential. These superhabitable worlds await our discovery, holding secrets about life, consciousness, and the nature of being that could redefine our place in this magnificent cosmos. Sleep well, fellow travelers in this cosmic story. The universe holds you, just as it has held every generation of stargazers who came before, and with the dawn, we will be one step closer to grasping the true splendor of it all.